Hello, everybody, and welcome to this live coding episode. Today, what we're going to be doing is we're going to be taking a look at how you can actually implement something called a character recurrent neural network from scratch to generate people's names. Now, before we begin, thank you very much, everyone, for joining in today. I do hope you're doing well. And the purpose of this entire series that I'm doing of coding live is to essentially make it so that people can learn different kinds of advanced technologies like machine learning from scratch in a super simple way with me. And today I'm joined by one of the best coder friends of mine. His name is Omer. Omer, would you like to introduce yourself before we begin?
Hi, my name is Omer Kamal. I've been working with Tammy for the last year, and it was a lot of fun. And I'm learning something new today is how to do machine learning with RNN, since this will be my first time actually doing it. So it's
Wonderful.
literally from scratch.
That's great. So, alongside everybody else joining on the stream, we're going to have Omer learning about recurrent neural networks as well. And of course, he's going to be helping us out with the actual implementation and the actual code. And I feel like we should dive right into what we're doing today. By the way, just so you know, since this is a live session, the whole point of this is that if anybody has any questions or any, concerns or even ideas of what to do, feel free to leave that in the live stream chat. We're monitoring that every so often to see what you're saying. And if you have any questions, we'll answer them. If you have any ideas, we'll try and implement them, and we'll be taking it from there. All right. So are you ready to get started? Wonderful. Okay. So let's start off with what we're actually going to do today. So here's my idea. We're going to take a recurrent neural network. So in this case, I'm thinking we'll use like an LSTM, probably just a single layer. And we're going to feed it a data set of approximately 6,700 names. Now, these names also have other information associated with them, for example, the gender of the name. And these names do repeat across the data set as well, so we're going to have to find the unique names. And then we use those names to actually generate new names with a character recurrent neural network technique. So, Omer, have you ever implemented like recurrent neural networks or character recurrent neural networks or tried that out before?
Oh no, I haven't tried anything with characters usually. It was
In
usually
that
just
case,
images.
we're gonna be starting from scratch. That's great. So just so you know, everybody joining the stream, what you're seeing on my screen right now is the Atom text editor, and this is where we're going to be writing all of our code and actually running stuff. Omer and I can both modify this at the same time, so we can both be coding, and you'll be able to see what we're doing. The green cursor is Omer's, the blue one, which you'll see in a moment, is mine. All right, so let's get started. Now, the first thing we want to do is, of course, talk about the data set and how exactly we're going to be doing the data pre-processing to get this to work. So on my screen right now, I've got my terminal open, and if I go into my downloads folder, there is a file that I can unhide called, well, let's actually see what all my JSON files are. Do we not have, oh, looks like I'm going to need to look at all hidden files too. No, does that not work? CH flags, maybe I can find it with curl. No, I cannot find it with curl, so I'm going to have to go back into my terminal history to find, okay, it's called cln.json. So what I'm going to do really quickly is get my file. There we go. And I'm going to show you what exactly this data looks like in Python. So one more thing that I will do is, there we go. So Omer, I'm gonna send this data to you so that you have a copy as well.
Okay.
And then you can take a look at it, and I'll show everybody on the live stream what exactly that data looks like. There we go. It's 35 megabytes of data. So there are 250,000 individual samples of names. And let's take a look at what they look like. So if we open up a simple Python 3 interpreter and we import the JSON library, then I can actually go ahead and load this in. So I'm just going to open up cln.json. Python loads this in pretty quickly. It's not too complex of a task. There's a single key within this JSON dictionary called results. And if you take a look at that, the length of that is 258,000. So we've got 258,000 results. Now, within the results, the schema of the individual elements looks something like this. So you've got the actual name as a string, you've got the gender, of course, and then you've got some other things like created at, updated at, and the object ID. Those are because this was actually grabbed from a database called Back4App. So there will be a link to that I'll post later, but if you just search up on Google Back4App name gender database, you will find this data set. So there we go. We've got that data set. Omer, did you get the data yet?
Yeah, I got it.
Perfect. All right. So basically, here's what I'm thinking. What we'll do is we'll go through this entire list of names. We'll find all the unique names. We'll lowercase them so that, of course, we only have to deal with 26 characters and no more. And then we will go ahead and feed those into a character recurrent neural network and have it generate new names. So before we even get started, I feel like it would be useful to talk a little bit about what a character recurrent neural network is, how it works. Omer, if you have any questions during this, feel free to ask me, and of course in the live stream as well. And then from there, we can get into how you can actually implement it. Sound good? All right. So here's what I'm going to do. I'm actually going to open up a little whiteboard so that you can see what I'm drawing over here. There we go. And as I draw, you should be able to see what I draw. That's good. So essentially, the purpose of a character recurrent neural network is to use the fact that recurrent neural networks can understand time series of data to actually generate new data. So the way a recurrent neural network works traditionally is, let's just say, like with a regular sort of multi-layer perceptron network, you would have your data, so let's just say X, and that data you would feed into your neural network, and you would have it predict some new output Y. And what a recurrent neural network does is it takes the hidden state of this neural network itself and essentially feeds it back into itself for every time step. And what that does is enables it to understand data over time. So think about it like this. If I were to, for example, give you a sentence like, this is a YouTube live show, right? So for example, if I were to write out, this is a YouTube live show. Then if you take a look at the sentence, the word show, for example, could have a different meaning based off of whether the word live came before it or something else. The YouTube live the word live could have a different meaning based off of what came before it. Are we talking about something's life? Are we talking about human lives? Are we talking about a YouTube live show? Context matters. And so in a way, what you can do is you can treat this sentence, you can treat this natural language sentence as a time series of data, where first you said the word this, then you said the word is, then you said the word a, and because each word's meaning is different based off of what came before and what came after it, you could count this as a time series of data. So first this, then is, then a, and so on and so forth. And essentially what a recurrent neural network does is, as I mentioned, tries to understand time series data by keeping the hidden state persistent across those time steps. So what we're going to be doing today is essentially putting together some classic sort of neural network techniques along with this new recurrent neural network technique to generate names. And the way it's going to work is this. Let's just say we want at least the network to generate the name John. All right, so pretty simple example. Instead of having this at the word level, as I was talking about before, we're going to count John as a time series at the character level. So each character, whether or not it should be there, depends on the characters that came before and after it. So what we're going to do is we're going to start off by saying, oh, well, there's nothing before a J, so let's just count this as a blank. All right, and let's feed this into the neural network. And then from there, the neural network would output, let's just say, J. That, hey, we want the next output to be J. because of course we're trying to predict John. Again, this is assuming that the neural network was trained to predict John. Then after that, what we're going to do is we're actually going to take this J and feed it back into this neural network along with the previous hidden state of that network, and it should predict an O. And then we're going to continue the cycle. So we're going to say, all right, so we predicted an O, so we're going to take that O, we're going to feed that back into the neural network and the neural network's previous hidden state, and then we're going to predict maybe an H. And then we're going to do that again. So this is just going to keep going and going until we reach the end of the sequence. So we've predicted John. Now, how do we know to stop at John? What's going to happen is you're going to feed the N back into the neural network along with the previous hidden state, and it's now going to predict a blank. And when you predict a blank, that means the neural network is saying, stop here, that's the end of the name, we're done generating. So that's essentially how this architecture is going to work. Is that clear, Omer?
Yeah, that's clear.
Perfect. Let's see if we have any questions from the live chat just yet. What encoder are you going to use? For example, one-hot encoding or building one with NLTK? Great question. So for the input to the actual neural network, obviously the data can't be an actual character like an H. So we're going to do what's called one-hot encoding. So we're just going to take the character, we're going to feed it into a little, I wouldn't call it an algorithm, a little technique that's going to encode it in something that's called a one-hot fashion. So since there are 26 characters in the English alphabet, we'll have an array of zeros, and that array will be 26 elements long. It'll have 26 elements within it, all zeros, and the index where the H is within that array, that's going to be a 1. Everything else will be 0 to represent that we are feeding a 1 into the network at that time step. So that's how the input's going to work. Output will work very similarly. We're going to output a probability distribution over each individual character. So each time step will have 26 outputs, and each output will represent the probability of that character being the one that should be plotted out or shown to the user. Now, there's some very interesting things that you can do with this network. So, for example, what you could do is you could do this example that I've just shown you, where you could feed in a blank, and then you could actually start from scratch and have the neural network generate, whatever it wants to generate. You can do things like, for example, being able to prime the network with an existing sequence. So, for example, you could feed it with TAN, and then after that, you could have it just generate from there. And then you could say, all right, now you can generate on your own, and you can see if it generates TANME or whatever else. Or you can even do things like conditional recurrent neural networks, where you can say, all right, I want you to generate, but assuming that the gender is a male or a female. So there are all sorts of things that we can do, but for now we're going to keep it really vanilla. We're going to be implementing from scratch this character recurrent neural network. Now, how do we process the data set for this, though? As with many things, the data is usually the most difficult part. The neural network is actually pretty trivial in a lot of cases. But what we can do is I'm going to go ahead and clear the drawing for now and sort of explain how we're going to be doing data processing. So first of all, let's just say we have two names, John, like this, and Smith. And let's also just have one more, let's just say Bahir. All right. Now, these are all names of different lengths. So we've got a name of length 4, of length 5, and of length 6. Now, what this means is that for these three names, we have to do what's called padding the sequences differently. So let's just say we were to, look at John and ignore all the other data. Then what would happen is we would end up creating an array that can be fed into the network of shape 426. So what that means is there are 4 time steps. So that would be the time steps, and remember each character is a time step, and 26 possible characters. Okay, because there's 26 characters in the English language. Now for Smith, you would have, 526, and that's a bit of a problem because if we want the neural networks to be fast, we would prefer if all of the time step dimensions were the exact same length. And so what we need to do is we need to do something called padding to make it so that John becomes the same length as Smith by just adding a bunch of zeros at the end, so that after padding we get 526 as well. But wait, 5 isn't enough because here would give us 6. So what we actually need to do is make it so that all of these pad to 626 like this, and I can erase this one over here because we want it to be 6. And then what you can do is you can actually merge these all into a batch with shape 3, 6, 26. So 3 samples with 6 time steps each, even though John is only 4, it doesn't matter because it's just padding, and then 26 characters in each time step. So there we go. That is how we're going to be processing. That's what we want the shape of our data to be. Now, how do we get it to be that shape, and what's it going to look like internally? Let's talk about that a little bit now. So yeah, go ahead.
The one question I do have is, you put 26 characters. Cannot,
Yes.
say, a name repeat with the same letters over and over? Or is that 26 not actually the character length?
So the 26 is this. Well, technically, it's not the character length; it's the vocabulary size.
Okay.
So there are only 26 characters in the English language. So when we one-hot a character, one-hot encode a character, then we only need 26 individual scalar values in the vector to represent that.
Okay.
And so yeah, so that's the shape that we want our data to be in. Now, in terms of the actual processing of the data, here's how I'm thinking we do it. So let's just say we've got the name John. What we do is we take the name John and we split it up into 2 different sets of data. So we have the input data and the output data that we expect from the network. The input data needs to be shifted to the right so that we can actually predict John. So here's what I'm thinking. We take John, and before it, we insert a blank, and then we pad it until it reaches our desired length. And that's our input sample. And then for the output, what we do is we take John, and then we add a blank at the end. Okay, so we add a blank. I'm just going to square the blank so you know it's just a single sample. And then we pad to the desired length. Does that make sense?
Yeah, that makes sense.
So then, just so that everybody can understand this a little better, let me see if I can actually take this. So if we take this, and if we, I'm not sure if I can actually move this. No, I can't seem to move it. I can.
Please do not scale it. It looks horrible.
Yeah, I mean, it looks like it's just going to scale, but we of course don't want it to scale. But if you were to actually take these and put these side by side, you would understand why I'm saying we should process the data like this. So let's just say I put the input in. So there is blank. Okay, and then we have J, O, H, N, and then pad, 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 just to get it to a standard length. And then if we put the output data right under that, you can start to see why I wanted the data to be processed this way. Okay, and then pad, 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 pad. All right. So each input has a corresponding output, which happens to be the very next input. Now, just a little minor side note is that, well, technically we have 26 characters in the English language, but the thing is we're actually going to need to increase this to 27 because the very last element has to represent this blank token. So this is index 27. The very final character would represent the blank token. And also, another side note is that for the output padding cannot be all zeros because the output will have a softmax activation, and softmax activations cannot predict all zeros. So we're going to need these to actually technically be all blank tokens, but the input to the network will be all zeros. All right. So here's what I'm thinking, Omer. Let's split this up into two parts. So we've got the data pre-processing and preparation part, and then we've got the actual neural network training part. So I'm going to go ahead and start implementing the neural network training, and in the meanwhile, at the same time, you can implement the data pre-processing to get it to a shape like this, where we just have X, Y, or input and output data sets that we can feed right into the model. What do you think?
Okay. I think that's good. As long as we get the data process, and then we can train it right after, as quick as
Sounds good.
possible.
Perfect. So what I'm going to do is I'm going to stop sharing this whiteboard in just a moment. Let's see. Okay, so really quickly before we continue, though, we have a question from Mustafa. He says, why the network would be fast if the time step dimensions have the same length? So I'm going to go ahead and stop sharing the whiteboard so you can actually see us now. And the reason that it would be faster is because, well, technically, there are two reasons. Or there are two notes to take. First of all, because of the way that we're training the network right now, it won't necessarily be faster. However, if you are training on a GPU or something called a TPU from Google, it'll be faster because then you can take all of your different names, which have the same time step dimension, and put them into a single tensor, batch them together, and feed them at the same time. If they have different values in the time step dimension, then you can't put them in the same tensor or the same array, and because of that, you can't batch them together before you put them into the actual neural network. What that does is it makes it so you have to essentially feed in your names one by one, and that makes it really, really slow. Now, what you could do is you could have multiple batches of the same time step dimension each, so you can do what's called bucketing your data. While you could bucket in this case, we're not going to because bucketing adds a layer of complexity to the data pre-processing that we don't want to deal with. Padding is a lot simpler because then the batching can be handled by the APIs themselves. And at the same time, when we do batching this way, we can shuffle around the data, and that way, different data from different parts of the data set are put together, giving us a more random sample and making it so that when we calculate the gradients, they're smoother because they're actually across from random elements across the whole data set. If you get, for example, a bunch of 4-letter names and you run gradient descent on those 4-letter names, and in the next batch you have 5-letter names, then suddenly there's a shift in that gradient that's pointing somewhere else. So it'll be smoother if you average across the entire data set instead of local samples. So let's go ahead and get started with the actual code, shall we? So I'm going to go ahead and show everybody my actual screen, but they can still see us, Omer. And now let's get started with coding. So I'm going to go ahead and handle my my neural network stuff, and you can get started with data pre-processing, and we'll sync up when we reach milestones. So just to confirm, Omer, can you still type on my thing? Okay, there we go. So I'm going to save this as name generator.py
Okay.
So that we can get started.
Okay. I'm just gonna do my code off and down the screen, and then I'll paste it in there once I'm done.
Perfect. In the meanwhile, let's actually get started. So we're going to be using PyTorch for this tutorial. I usually have more experience with TensorFlow and Keras and those kinds of frameworks. However, PyTorch is something that I have been really very interested in because the way that it enables you to be a lot more dynamic in the way you represent your computation. So we're going to start off with PyTorch code, and we'll see how that goes. We'll be using a lot of documentation and Stack Overflow and things like that. And from there, we can see how we want to continue implementing. So let's get started. So we're going to import PyTorch, and I'm going to assume that we have a function called load data that we can just call, and it's going to return the data that we need. Now, for now, so that we can actually work, I'm going to put in like a little placeholder here. So I'm just going to return a random NumPy array. So we would have random inputs from 0 to 1. Where the input shape would be, let's just see here. Let's just say we have 6,700 samples, and each sample is 12 time steps long. Also, Omer, one more thing that I want to clarify, and this is clarifying for everybody else as well, is that the data set, the longest name is 11 characters, but the longest sequence in the data will have to be 12 time steps. And the reason it has to be 12 time steps is because we have that blank token as well that we need to account for. So the longest one with 11 characters will have no padding, but a blank token in the beginning for the input and at the end for the output. But everything else will be similar, but with a lot of padding at the end to handle it.
So it'll be 13 in total, right?
No, 12 in total. So the longest is 11, 12 in total. Because the blank token is either in the beginning or at the end. For the input, it's in the beginning. For the output, it's at the end.
Okay, and then for any other ones, say we have character length 9, we have one in the beginning and one at the end?
Yeah, and then after you insert in the beginning and the end, then you pad at the end. So the output, it'll be the name, the blank token, and then the padding, not name, padding, blank token.
Okay. So assuming we always pad at the beginning, if we have any space left, we just pad to character 11.
Exactly. Or till character 12.
Yeah, 12.
Perfect. All right, so good that we got the data shapes cleared up. Now let's actually get started with real code. So NumPy random uniform from 0 to 1, you can go ahead and implement in this function while I go ahead and work on the actual neural network stuff. So in order to represent this neural network, I'm wondering if we should actually code in the LSTM self from scratch, or if we should just use the one that PyTorch gives us. Now, I'm going to start off by using the one that PyTorch gives us. If we have a little bit extra time, then we'll go ahead and implement the actual cell from scratch as well, since I feel like that would be really insightful, and because performance won't suffer too much because we have a very, very small data set to work with, which is why this is great. It's a small data set, but it's a real example, so we can train it directly on MacBook Pro CPU, but at the same time, it teaches you how these networks work. So let's take a look if we have any questions really quickly.
You just said MacBook CPU or GPU?
Well, technically, this MacBook does have a GPU, but it's AMD, so we can't really train on
I
OpenCL
don't
right now.
know if PyTorch will work with Mac GPU. If it does,
It
it's
does
amazing,
not.
but I don't know. I don't think TensorFlow even does. Only
No, it does
CPy
not.
itself.
There is experimental support for what's called I think it's called AMD ROCm, which is like the AMD competitor to CUDA, as far as I know. But I'm not completely sure. So this is how we're going to start off. We're going to have a class called the Name Generator module, Name Generator model, which is going to inherit from torch.nn.module, which is how you would define your neural networks in PyTorch. And of course, there's going to be a little initializer over here, which takes self. I'm not going to take any hyperparameters right now because I'm just going to hard code them in the class. Of course, if we wanted this to be more generic code, then we would. Then we would actually have it take the hyperparameters and insert them into the model, but for now we're not going to do that. So, of course, PyTorch does have it forces you to call the super initializer first, so we're going to call that really quickly before we actually start our initialization. Then we can actually start doing stuff inside the model. So we're gonna go ahead and inside of this initializer, we're going to initialize two layers: the LSTM layer and then the neural network layer that will take the LSTM hidden states and predict the characters that we want from them. So we're going to have the RNN layer would just be torch.nn.lstm, and if I remember the input correctly to this, it should be something along the lines of 27, 128 would be the hidden size, and that should be all. We shouldn't need anything else. It should be that simple. And then I'm also going to do one more called H2O, hidden to output, which is just going to be a linear layer from 128 to 27 again. And then finally, we're just going to do we want to get a softmax here? Yes, we do. So we're going to have a self.softmax, which would be torch.nn.softmax. And the dimension that we want this to be on would be 2, because our shape would be batches, time steps, samples, and so we wanted to run softmax on the samples axis. So 0, 1, 2. So that should be our input. Let's see if anybody has any questions about this. Someone asks, is it possible to use NVIDIA GPU with Mac? Unfortunately not. Apple, for some reason, does not support NVIDIA drivers on Mac OS. NVIDIA does have the drivers, but they're not being signed by Apple, so they're not supported on Mac OS. Apart from that, someone says, how to integrate time series data and spatial data? Please explain. So what I would say is before you think about integrating time series and spatial data, there is a tutorial of mine that I will link in the chat right now. And essentially this tutorial is about something called the unsupervised sentiment neuron, which is something that OpenAI worked on. And this tutorial explains pretty much in depth how LSTMs work, specifically something called a multiplicative LSTM cell. And when you understand how LSTMs work a little more, then you'll understand that within the actual LSTM sort of recurrent neural network cell, there are a number of linear operations that take place. And if you were to swap out those linear operations with convolution operations, then you can understand spatial data over time. So if that's what you meant, understanding spatial data over time, then that's one way you can do it. But please do let me know if that answers your question. But I would, again, recommend understanding how recurrent neural networks work first. And I've linked to that tutorial in the chat. All right, so now we can get back to code. So we have the initializer ready. Now we're going to define the forward pass of the model. It's just going to take the input, which would just be x. We're just going to call it x. That's the standard that I've seen people calling it for PyTorch code. And the x, so x will be a tensor of shape, batch size, time steps, and then samples. So in this case, let's just say our batch size is 32, number of time steps would be 12, samples would be, say, 27. Now the thing is, the LSTM expects something called time major data, which would be 12, 32, 27, so we're going to need to reshape the tensor, and I'm just going to do x.view for that, so x.view, x.shape, 1, x.shape 0, and then -1 for however many samples there are. So I did see in the chat someone said that you could just do data.shape to make it more dynamic, and that's what we're doing. It's just to help us conceptualize what that data looks like so that we can actually code it in. We are going to be sort of filling in those placeholders, but then actually within the code, we will be using the .shape command to figure out the shape dynamically. So in this case, you could feed the forward network with any number of batches, any number of time steps, and it would still work. The only hard-coded part is that the number of samples needs to be 27. So the number of individual characters, the vocabulary size, needs to be 27. So we're just going to get the view, which will just reshape. That should automatically fix that. And then we can just pretty simply do self.rnn on x, and we should suddenly have a tensor of shape. Let's see if I get this right here. 12, 32, 128, which would be our hidden size. And then we can feed that into our linear layer, which would be hidden to output. And then we can just return softmax on x. Should be pretty simple. Now, just in case you're coming from a Keras world, this might confuse you a little bit, as it did for me a couple of days ago when I was getting into this, because the recurrent neural network is returning time major data, so there's 3 dimensions to it. But then how are you feeding those 3 dimensions into a linear layer when it should only be taking 2-dimensional data, which would be batches and samples? The interesting part about PyTorch is that it supports 3D inputs for your dense layer. So what it'll do is it'll actually convert the 3D to 2D, run the actual dense layer, the linear layer, and then reshape it back to what you expect and then return it to you. So it's kind of like how if you were to wrap a Keras dense layer in a time-distributed wrapper, PyTorch handles that for you. If it detects that you fed in data that is time distributed, then it'll automatically time distribute the linear layer for you. So that's gonna happen automatically. So the actual model portion of this was pretty simple. Next up, we have to define our loss function. Now the loss function is where things kind of start to get a little complex, but we're going to keep it super simple. And for that, I do want to know how exactly categorical cross-entropy loss is implemented. So let's take a look at that. So I'm just going to open up Safari, and let's try and figure out how categorical cross entropy is implemented. And let's do that with NumPy. So I feel like this one would be good. I've used deep notes before and they have good content. So if we scroll down a little bit, okay. So this is an implementation of cross entropy loss with NumPy. So let's just see how this works. So essentially, if I'm understanding this correctly, what's going to happen is you're going to take the softmax output of your neural network, so the logits, and then you're going to get something called log likelihood, which is from every output, get the correct sample's probability, then find the log of that sample, so feed that into the log function, negate that, and then that's your loss function for that specific sample. Now, of course, because we're dealing with a lot of data, we want to average it across both the timestamp dimension and then the batch dimension. The question is, can't you use a built-in loss function like categorical cross entropy? Yes, we can, but there are two things. First of all, I want to implement this more from scratch. Second, I don't want to deal with having to, with potentially PyTorch not liking the 3D data for the categorical cross entropy and that becoming a source for bugs later that would be difficult to find. Because the loss function is simple enough, we might as well just implement it ourselves. But of course, if it were more complex, you could easily go to the PyTorch documentation, figure out how the loss function works, and use it correctly. It's just for now, I feel like it would be valuable to implement that as a simple function. So let's go ahead and do that. So cross entropy loss, and it's going to take y hat and y. So y hat being the prediction, and y being the output. So there's one thing in this implementation. Y, which is what they expected, was sparse. It wasn't dense data, so it was not one hot encoded. But in our case, it will be one hot encoded. So instead of doing this like slicing the NumPy array, the way that they sliced it, what I'm going to do is I'm actually going to multiply y hat by y to mask the outputs to the correct sample, and then once it's masked, I will get a sum across the sample dimension, which will do essentially the same thing that this little snippet of code would do here. So let's go ahead and figure out how to do that. So I think there should just be a torch.sum function or something of that sort. Let's see. So torch.sum, search the documentation here. All right, so there is a torch.sum function, but it's going to return the sum of all the elements. We wanted to do the sum across a specific axis. So, okay, so there is a function for that. So you feed in the input and you give it the dimension across which you want it to calculate the sum. So I think all we should need to do is torch.sum and then feed in a -1 at the end, and we should have the masked probabilities. Again, because every other element will be 0 and only the correct one will be the actual probability, it'll essentially do the same thing as what they were doing with the deep notes implementation. So then from there, we have our masked probabilities, and we just calculate the negative log value. So let me see if torch has a log function here. Torch.log. Or can we just do math.log on a torch tensor? Torch log tensor. Let's see. Let's search for this implementation here. Okay, it looks like there is a torch.log function. And this is where the Python REPL becomes incredibly handy to try this out. So what I'm going to do is I'm just going to import torch really quickly and just generate a random tensor with shape, say, 5. So super simple. And do we have torch.log as a function that's available? Yes. And when we run that, that works, which just to confirm that we're using the right thing, if we were to do np.log, we should get the exact same output, which we do. Very good. So torch.log is the correct function to use, so then we can just say log probs would be negative torch.log for the masked probabilities, and then just return torch.sum of the log probabilities, but then we want to divide it by the number of log probabilities there are. I'm going to confirm that that's what we want to do. Yes. So divide that by y dot shape. Would it be 0 or 1? I think it would be 1. Or simple log probs dot shape 0. There we go. So that should find the average negative log probability of the correct sample in the output. And that is going to be our loss. And just like that, we know what our loss function is. And of course, what's absolutely amazing is that when you actually run this code, what's going to happen is PyTorch is going to go through this, and as you run the code, it's going to build this little graph internally of the actual code that you're running. It'll be actually calculating the values of those tensors eagerly. So whenever you print out in between, you already have the values calculated. But then when you calculate the gradient of that graph of operations with respect to a certain variable, it'll be able to do that really fast, and it's dynamic, so we don't need to worry with statically compiling a graph like the old TensorFlow would have you do, things like that. All right, so we have the model, we have the loss function, now we have to write a training loop. And after this training loop, then we'll see how we can start to improve the model and see if it actually works on some dummy data while Omer works on implementing the data preprocessing. So let's get started with that. So in the training loop, what happened, Omer? Are you stuck on something?
No, I just hate the shape of the data. That's
Oh,
it.
you hate the shape of the data? What's wrong with the shape of the data?
Is result, and inside result is a list of maps. I'm trying to get that to work.
Uh-huh.
I haven't done that before, but seems to be fun so far.
All right, well, hopefully that works.
Just using Panda.
Mm-hmm. Yeah, pandas should make everything a lot easier. Now, again, I've already said this, but just something to keep in mind is that there's 258,000, I believe, names in the data, but they do repeat, so you're going to have to find the unique names, lowercase them, then process. So,
Okay, that's fine.
yep. So now the training loop. We can actually probably do this outside of a function, just within our Python script. Now, of course, since I kind of want to be good with the quality of my code here, I am going to put a main guard just to make sure that we're not like importing this file somewhere, and then call a training loop function, and then define that over here. And then we can do whatever we would want to in this little script part. So within the training loop, all we would really need to do is say we have a new model called the Name Generator model. We have an optimizer, which would be in the torch.optim module, and we want it to be an Atom optimizer, and we're going to be feeding it the model parameters. And I'm going to keep the learning rate at the default for now, but we can change it if we think the training is too jittery or something of that sort. So there we go. We have the model, we have the optimizer. What else do we need? Well, let's define some hyperparameters, shall we? So we've got something like a batch size, and I guess we will manually. Well, we don't need to. We can actually have PyTorch batch the data and feed it to us automatically. So I believe we would use something called a data loader to do that. But first, we would need to convert the actual NumPy array to a torch tensor, and then from a tensor to a variable. And then we would feed that variable into a tensor dataset, and then the tensor dataset would go into a dataset loader. So let's try and figure out how that API works. Let's see, PyTorch dataset example, and then we can copy that from there. Okay, so this data loader takes a dataset and a batch size. That's pretty standard. Now let's figure out how the tensor dataset works, and then we will find, I think it's torch.autograd.variable is where it's located. Or is that not it? Let's see, torch variable. Yes, it is in torch.autograd. So all I would need to do is say from torch.autograd import variable, so we can actually track operations. And then I don't think we'll need to import anything else. We can just call it manually. So we would say x, y data would be load data. and we can feed in a file path later, but I'll just go ahead and feed that in right now. All right, and then just for the sake of it, so that we know what our data looks like, we'll print out the shapes. Then we'll go ahead and convert that to tensors. So X tensor would be, or well, technically variables. X variable would be variable torch.tensor, and we would probably just feed in X, and that should be it. And then we do the same thing for Y, like so. So we have X, we have Y in variables. Now we create a data set. So we say data set would be torch.utils.data.tensor dataset, if I'm remembering the API correctly. And then we just feed it whatever tensors we have that we want to be part of the data set. And then the data loader would be torch utils data loader. We would feed it the data set, and we would say the batch size would be like 32. So approximately, rough estimation, we would have around 209, 210 batches of like full batches of 32 size to work with. So that should work out correctly. Well, I missed out data loader, but apart from that, I think we should be good to go. Let me make sure that the data loader is what it's called. Yes, it is. We should be good to go. Are we shuffling the data? I feel like we might as well shuffle. So let's go ahead and do shuffle true, since that might end up helping us out. All right, let's see. We see a question: do datasets have any effect on relative accuracy between two different deep neural network models? I'm not completely sure if I understand your question correctly. Please do make that a bit more clear. But my interpretation currently is, would, if I were to have two different data sets on two different neural network models, will they perform differently? Well, the answer is obviously yes. But maybe you mean, would the same data set perform differently with two different neural network models, or would the same neural network model perform differently with two different data sets? If you could explain that to me, that would be great, because then I can answer your question more accurately. But let me know, and we can get into that. Okay, so in the meanwhile, we've got the data loader, and here's the good thing about PyTorch. PyTorch's data handling is like hundreds of times easier than TensorFlow's, because the TensorFlow data class is just very annoying to deal with. All we need to do is loop through the data loader. Watch this. Okay, so just like that, you've got your data, and you can loop through your batch. It was that simple. Now, of course, what you would want to do is loop this inside of another loop for your epochs. So for epoch in range 10, something of that sort, let's just say we want to run 10 epochs, then you would loop through your batches, calculate loss, calculate gradients, do your steps, and you should be good to go from there. So we have our X and Y data. Now, all we should really need to do is say prediction equals model on batch X, and then calculate the loss, which would be the cross entropy loss between the prediction and batch Y, and then calculate gradients by going backward and then do an optimizer step. But I do want to make sure that the API calls are correct. So let me just search up PyTorch optimizer step, and we will make sure that that it works, that I'm implementing it correctly. Okay, I do believe it is working. Good. Okay. So the optimizer is defined correctly. The only other thing that I need to do is tell it that the optimizer at the beginning needs to have a 0 gradient. Otherwise, we're going to be like accumulating gradients across all the batches and stepping, and that's not going to be good. So we clear out the gradients, calculate the loss, and go backward. Step with the optimizer. Super simple. So that should be it. The only other thing that I'm going to do is store the losses across each batch within the epoch. So I can do losses.append loss.item since it's a scalar, and then find the average by just doing print, what would it be, sum losses divided by length of losses, and that should work from there. Okay, so this should be all for the actual training loop. Now we'll implement the data generation, like actually having the neural network generate in just a moment, but that's all for now. So Omer, where are you at currently with the data pre-processing work? Oh, you're muted.
So I haven't really figured out how to convert it. So what happens is every time I'm trying to convert it to a series from a data frame, and then I'm trying to go back and convert it back to some series. So I'm just loading it as a JSON and just doing it from there.
All right.
So I'm just ditching Panda completely.
All right, sounds good. So how are you doing in terms of like actual code? Anything logically that's tripping you up, or is it all good so far?
No, everything's fine. Just trying to get this data to actually look nice.
Nice. So once you have the data in the shape that it's supposed to be, let me know, and then we can go ahead and implement the actual like training of the network itself. Maybe what you want to do, since I'm done my actual model part, if you could actually paste in your code back into the shared Atom session, maybe you could explain your code as you're writing it.
There's nothing special at the moment.
No worries at all.
Just give me a couple minutes, and you can explain some other concept.
Sure, no worries. In the meanwhile, I will show you how you can actually generate data with this trained recurrent neural network model. Then we'll come back to Omer once he's done his data pre-processing part. So, okay, let me see. The question that I was answering a bit before that I was confused about, I got the interpretation. So, if a deep neural network model, neural network A, produces higher accuracy than another deep neural network model for a given data set, will neural network model A always produce better accuracy than net B for any data set given that all the other parameters are constant? That's a very interesting question, and the answer is no, you cannot be sure that network A will always be better than network B. The reason for that is because neural networks are more complex than just like individual multiplication operations. It's not like there's one kind of unit and just having more of those units or deeper of those units is going to have different performance of your model. What's really happening is you have all sorts of different operations and different kinds of modules within your network that are working together to create a classification or a regression or whatever. And the thing is, all those individual modules are good at doing individual things. Convolutional neural networks are good at finding local features and sometimes aggregating them into like global features and spatial data. Recurrent neural networks are great at understanding time series. Specifically, long short-term memory networks are amazing at understanding data over a very large sequence and knowing when to forget things and when to remember things. Gated recurrent units are good at things similar to LSTMs, but they're less computationally expensive. Peephole LSTMs are good at understanding very precise timing. So there are all these little different kinds of modules that are involved. And when you have all these different kinds of modules, it's always possible that on one data set, a certain
right, can you say something now, Omer?
Can you hear me now?
Yeah, I can hear you. Hopefully everybody on the stream can hear
Is
you.
there any way in NumPy to just get the greatest length of a string or in like a list?
There is. I'm not sure if it's built in. By the way, everybody on the screen, tell me if you can hear me now. If not, do let me know. Now. Well, so in order to get the longest length, I'm not sure if there's a NumPy built-in function, because if you have different lengths, then it's going to be stored as an object array, so an NP array of lists. So I'm not sure if it would be built in. But you can just assume that the longest name is 11 characters and that we want it to be 12, because I've already gone through the dataset and that's the longest name there is.
Okay.
All right, so someone says perfect, so I'm assuming people can hear me now, but hopefully you can. Now, unfortunately, I went on quite a bit of an explanation of how neural networks are deterministic and why we're structuring or how we're dealing with like perfect names. But I will explain that once again just to sort of help you out here. So, in brief, neural networks are deterministic. There's some kinds of neural networks that are stochastic, that are random. So, for example, mixture density networks are a great example of neural networks that generate variables that are fed into a function that generates a probability distribution based off of those variables, and then you sample from that distribution. But in our case, it's purely deterministic. And what that means is there's always what's going to be called a perfect name. So if you were to feed in a blank token to the network and then take the output and feed that back into the network with the argmax, so the maximum probability output at each time step, then you would get what's called the perfect name, which is just the name that the network thinks is most probable to occur. And a few weeks ago, I did a similar run, and the output, the perfect name was Ari, A-R-I. So it would be interesting to see what perfect name we get this time, and I'll also show you in a moment how we can make this more stochastic, so that it's actually generating new names and not just repeating the same name over and over again. So that would be interesting to see. All right, let's see. How to interpret the neural network model when validation accuracy oscillates for each epoch. So I will answer that in a moment. Let's first get to the training loop phase, but I will remember to answer that. So we'll get to the training loop so that you can actually see our validation accuracy. Once you see our validation accuracy, then we will get to your question, so that I can show you actual examples. All right, so in the meanwhile, so Omer, I see you're starting to load some code into the load data. I'll hand it over to you to explain how that works in a moment. For now, I'm going to implement the actual data generator, though.
Yeah, that's fine. I'm just trying to actually get this into a char array, and then I'll path it right after.
Perfect. So one more thing. So also, thank you very much for all the questions, everybody. Just so you know, quite a few questions, including this validation accuracy oscillating, came from Astronomy with Manas, so thank you for that. Apart from that, we have quite a few other questions, and in case there's anything that I do not get to, feel free to either repeat that in a moment when I'm doing something more related to that specific question, or I will be getting to that in a moment. So there is a note from Ion's Awesome Facts that says you could store the names you predict in a list and have it not predict any names in that list. Well, you could, but then you would need to implement the logic of how do you tell the neural network not to generate a name in the list. So what you could do in order to generate every possible name is generate the perfect name, and then based off of the names that you've already generated, make the probabilities for the characters that already occur in that sequence 0, and then continue from there. Although that would be really complex and really computationally expensive, so we're just going to do it in a stochastic manner, where it's like every time you call the function, it'll give you a different name randomly. So we'll do it that way instead. All right. So let's get started with the actual perfect name generation. So I'm going to create a function called perfect name, which will take the actual model itself and help us generate a perfect name. And after this, we'll take a quick 10-minute break. Omer will be done with his data loading by then, and we will be right back, and we'll actually go ahead and implement the training loop. All right, so perfect name. How do we generate a perfect name? So the first thing that we're going to need to do is we're going to need to keep track of the hidden state of the recurrent neural network across time steps, obviously. And the initial hidden state is always just going to be all zeros. That's how recurrent neural networks work, all zeros. So in this case, our batch size is just going to be 1. So we should just be able to do hidden equals torch.zeros, 128. Or maybe we don't want to do it that, no, we do want to do it that way. Now, the only thing that does kind of concern me is how exactly we are going to deal with the output of the LSTM cells. So there are 2 ways that I could do this, or solve this problem. There's the normal way, which is to go to the PyTorch documentation and just figure out what the output shape is of the LSTM. Or there's the interesting way, which is implementing the LSTM cell from scratch and using a for loop to loop through the actual time steps. So I feel like we're going to do it the interesting way for the sake of the live session, and we'll actually implement the LSTM cell, because I feel like that'll give us a much better understanding of how the LSTM actually works, and so we can do that way. Now, I was working on a different project a little while ago, which essentially forced me to write a custom implementation of an LSTM cell. So I'm going to open that up, since obviously I don't have LSTM cell operations memorized, and then we'll try and port that code over to PyTorch, since that's currently written in Swift or TensorFlow, and then we will train with the custom LSTM cells so that we have complete control over how exactly the iterations of each individual time step is done. So let's do that. So we're going to implement a new class called LSTM cell, and just so that this doesn't override with, it won't, never mind. And this is going to inherit from torch RNN module, and within it, we should just need to initialize with the input size and the hidden size, which will just be 2 integers. Shouldn't be too difficult, like so. All right, now we need to initialize our weights. Now the weights, the way they're initialized would be torch rand. We would want it to be input size to hidden size times 4, and I'll explain the shapes in just a second. Hidden size, and then bias. Okay, so we have our weights. Now let me explain how these weights work. So within an LSTM cell, there are 4 gates. There's input, forget, update, output. Yeah, so IFUO, input, forget, update, output. So 4 cells, 4 gates. Each gate is essentially its own linear layer within the cell, so its own dense layer. Now, the way the LSTM cell works is we have one layer that will map the input to the output for each one of those gates, and then another layer that will map the hidden state to all 4 of those gates' outputs. And then those gates will tell us how to modify the hidden state so we can actually remember or forget or update data in a specific way. Now, there's also a bias, which of course is just regular linear layer stuff, a bias for each of the gates, so hidden size times 4. I'm just going to fix this little typo over here, and then we're going to implement the forward pass. So the forward pass would have self, and we should just be feeding an X. Now we are going to actually, now that I think about it, we're going to have it done a slight bit differently. We're going to have the time step input, time step hidden, and time step cell. Okay. Now this is where the other code that I've written before would come into play, because again, I do not have the bandwidth at the moment to memorize LSTM cell operations. Who does really? So we're going to copy it from this previous implementation that I've written for a different project altogether. So essentially it's going to work like this. We feed the input into IH, so TS input, like so. We add the result of the hidden, and then we add the bias. That should be it. Well, there is a we would actually need to do a matrix multiplication. Sorry, we cannot do it that way. We have to do a matrix multiplication because the torch.ran tensor is a tensor, not a layer. So we have to do torch matrix multiplication. I do believe it should just be torch.matmul, and we'll just try that out and see. As a matter of fact, we could just use the Python interpreter to figure it out. Yeah, that's right. So all we would really need to do is say torch.matmul matrix multiplication between the input and the weight, and same thing over here. So torch.matrix multiply between the hidden and the respective weight. So let me just make sure that's the correct implementation. It does seem to be the correct implementation. So I'm just going to move this over here so it's a little easier to deal with. And that should be our z variable. All right. This implementation, by the way, that I've written is very, very heavily inspired, almost directly ported from the implementation of the LSTM cell in Keras. This is the GPU accelerated implementation, so it's super simple. It's its own implementation in the Keras library. You can take a look at the Keras source code if you want to find out how it works. Okay, so let's see. There's another question again from Astronomy with Manas. He says, in some cases, yes, but not always necessarily true. Neural network will try to learn latent or hidden features in the data. The latent space is different between data sets. I'm not sure what exactly you're referring to at the moment. Tell me what exactly it is that you were referring to with that comment, and I'll comment on it in a moment. All right. So back to implementing the cell. Now all it should really be is just slicing our state in a certain way and then processing it. So let's go ahead and figure that out. So Z0 would just be we would be slicing it from 0. Well, we could just put a colon because in Python slicing is a lot easier. And then we want it to go up until self.hidden size. All right, and we actually have to store that within self in the initializer. All right, there we go, self.hidden size. Then what we want to do, well, we would need to put a colon before that to go up until self.hidden size. And then we just continue this pattern like so. So we do self.hidden size to self.hidden size times 2, and then times 3 from times 2, and then just times 3 onwards till the end is what we're going to say there. That should give us the correct sort of gates outputs to work with, and then we can actually calculate the outputs of the gates. So I would just be torch.sigmoid Z0, F would be torch.sigmoid Z1, I believe. Let me just make sure that's correct. Yes, forget would be Z1. Then the C, which I believe is also called the update gate, would be the forget gate multiplied by the input cell state, and then you add the input multiplied by the sigmoid of Z2, so that update gates output. And then finally, or well, we'll keep the naming consistent, we'll call it C, and then O would be sigmoid Z3, like so. And then all we would need to do is say H is equal to O times torch.10H, I believe is the function, for C, and then return H and C. So just to fix this up, this should be a valid implementation of an LSTM cell. Of course, when we're actually training, we'll figure out if that's the case. But there is one more function that we still need to implement at the moment, which is forward across time steps. So this is going to take in, this function over here is going to take in the input for the time step, the previous hidden state, and the previous cell state, and then return the new hidden in cell state. However, we need to create a function that can actually run this cell on time major data, automatically looping through and calculating all the outputs. So we will do that in a moment. For now, I'm going to give Omer a little bit of time to work on the data pre-processing, and I will be back in approximately 5 minutes so we can work on the LSTM cell implementation. So we'll be back in 5 minutes, and we will continue with our live code. All right, we are back. Sorry for the delay, but now let's get into the actual coding of the network. In the meanwhile, Omer has gone ahead and implemented some of the data pre-processing. I sort of provided a bit more information of the actual like shapes and stuff that were necessary. But in general, what's happening here is we have this function called onehot, which just takes a name, so literally any string. And it will generate the data as I had explained towards the beginning of today's episode. And so specifically what it'll do is it'll take the data, it'll go ahead and one-hot encode all that data. It'll put it into two separate arrays, one input and one output. In the input, it'll insert a blank in the beginning. For the output, it'll append a blank to the end, and then both will be padded to be at least 12 elements long, or at maximum as well, 12 elements long. And then we'll return both the input and output data, and this function over here goes ahead and actually does the one-hot encoding for all the names. So let's go ahead and actually work on the training loop now. So as I mentioned, we've got the LSTM cell. And within the LSTM cell, we do have the function that will be responsible for taking... Oh, one thing I just remembered is that I actually have to show you the code. There we go. Now you can actually see code. So again, this is the code that's responsible for data loading. Omer, anything else you wanted to say about the data loading so far?
Not really. I tried to do everything in using Panda, but I always found I was finding issues when trying to convert it into a data frame and then get the data to go. So I just converted load as to JSON, get the result, put it back into the data frame, and then got the unique names quickly from it. I found this to be more efficient than trying to work with data frames, where I haven't done that for such a long time. So that's where I was kind of stuck on for a while, trying to really get this to work with data frame completely, but I guess old-fashioned, just load it as a JSON and work with that is much better.
Perfect. All right, so thank you very much for this little data generation portion. Now we can actually get into the training, but just before we do that, there is one more thing we got to do, and that is the recurrent prediction function, which will basically just take a bunch of inputs, so multiple inputs, and it'll predict across the inputs. So the way we're going to do that is we're assuming it's in time major form, and we should just be able to do, let me think, we would want to get the time steps, which would be inputs.shape0, and then we'd want to do for I in range time steps, and then from those, and then within that loop, we would get the current time step, which would be this, and then we would also want to define TS hidden and TS cell as well, which would just be torch.zeros, one self.hidden size, and same thing for cell over here. Then what we want to do is basically just TS hidden, TS cell equals self. So we're calling our self, we're calling this forward function, and we're going to pass it TS input, TS hidden, and TS cell. Okay, so that should fix a lot of our issues, and we should just be able to return an array of all the hidden states by doing hidden states is an array, and of course we don't want to make this another list, so we just do hidden states append TS hidden, and there we go. Okay, so that's the recurrent prediction function. That should help us out with the actual prediction across time steps. And now we just replace this with our custom LSTM cell. And from there, we would want to call dot recurrent prediction, because this is assuming that we're going across a whole sequence. And I feel like what we can do is go ahead and actually try out training, see what our loss values are like, and then we can come back and implement the name generation. All right, so let's see over here. We've got the training loop mostly ready. I think that we should just be ready to go and actually run this code. We'll implement the perfect name in a moment after we try this out. Let's go ahead and try. So I'm going to run Python 3, what do we call it, Name Generator.py. Let's see what it says. And of course, there is a good chance that we've messed something up in the first try, so let's go ahead and figure out what went wrong. LSTM cell doesn't have parameters. Well, of course, that's because we didn't call the super initializer. Like so. JSON is not defined. Well, simple fix, simply import JSON. What else? We expected a scalar type long, but got scalar type float for argument number 2. What exactly was argument number 2? Line 48. See, this is the kind of bug that does kind of confuse me. We should have gotten, we should have expected both floats. And I feel like the way that we could try fixing that would be, let's just start off by printing out the shapes of TS input and hidden, and then we'll take it from there. Okay, so, okay, that's the issue over here. We are expecting it to be 32, so we want 32 128, but we're actually getting 128. So where exactly are we calling forward? We're calling it from here. So what we actually have to do is put in the number of batches. So that would be inputs.shape1. Like so. And now it should dynamically adjust the hidden shape based off of the batch size. Okay, so the shape issue is more than likely fixed, but for some reason it's still expecting a long, not a float. Now the reason that's confusing me is because, one sec, let me just print this out, is because for matrix multiplication, you'd be expecting floats, not longs. Omer, have you ever encountered a matrix multiplication that expects longs and not floats?
No, I think by definition it was also always like float, because when you multiply, you might... It depends. If our input are not long, or they're all long, it might expect that.
Potentially.
Because there's no... Because if you multiply too long, you're surely getting a float, so it might assume that.
Yeah. Well, I feel like the much easier solution is to avoid using matrix multiplication altogether and just use a linear layer instead. So let's go ahead and do that, because we don't want to finagle around with fixing PyTorch issues right now.
It does.
Now, we do not want a bias node, though, so keep that in mind. These gates should not use biases, so we just need to find the torch NN linear documentation and then tell it not to use bias. So it should just be bias is false. And then I should be able to do a very similar thing for the other cell or cells, and then I should just be able to do self.hh and pass this in, or self.ih and feed in the input. Now, it's always possible that it wasn't a matrix multiplication issue and it was really just a symptom of a larger issue within the code, but let's see what happens. Ooh. Still does expect longs. So what that's telling me is that there is indeed a more, a different issue. I would think, yes, torch.zeros is going to more than likely generate longs by default. We have to convert that to float. All right, let's try that out. No, that did not seem to have fixed it. Do we need to convert the numpy array? The numpy array needs to be converted to floats as well. There we go. Let's try this out. There we go. We fixed that issue, but we have another one. List object has no attribute dim. Let's see where that is. So in H2O, which is line 85, over here when we're calling the next dense layer, looks like we have to do a torch.stack to convert that list back into a tensor. Okay, very close. We're incrementally going through all the functions and solving these issues. Now line 89 has a bit of an issue. Okay, so it looks like y is not time major, which is why it's not really cooperating. So we've got to reshape y to also be time major. So batch y shape 1, batch y shape 0, and then -1 for everything else. And now in theory, I'm pretty confident that we should get loss values, even if those loss values are nans. At least we've fixed the errors that we saw so far. Now let's try and figure out where we're getting nan values from, shall we? So how do we go about debugging this? Okay, simple issue. It's because we're dividing by 0 because I forgot to or never mind, that's actually not the issue, I think. Let me actually go ahead and print out all the individual losses per batch to see if those are nan, or if we're getting the nan when we're calculating the average of those. No, it looks like they are all nan, and the first one, the very first one at least, was infinity. Let's see why that would be. Let's see over here. What could be causing us to get nan values? How about in between execution, we go ahead and print out the
Hey, Tammy, are we back in a second, okay?
All right, sure. Okay, so it looks like we're getting nans within the actual recurrent prediction itself. More than likely, these are surfacing due to issues in the forward function. So there's some sort of bug here that we're unable to see currently, but we'll be able to see it in a moment. So I'm going to go ahead and print out z, see if there's any nans there. Essentially what we're doing is we're tracing back to the origin of where we're getting these nans. Looks like we're getting it in z. Why are we getting it in z? Let's try and figure that out. What about TS input? What does that look like? Any nans there? Shouldn't be any nans. If there is, that would be very confusing. Okay, no nans, that's good. What about TS hidden? Let's take a look at that. Oh, hidden does have a bunch of nans. That's our issue over here. So it looks like when we're feeding our hidden state into the network, we're feeding it a bunch of nans for some reason, which of course we do not want to do. It could be that this extra float conversion might be causing that, although I somehow doubt that that's the issue. So let's see if that is indeed the issue. Did not seem to be it, as I estimated. One thing I could potentially do would be, instead of this whole thing over here, I could just do inputs.new to create a new tensor on the same device as inputs, and then call 0 on it to zero out all the values. I feel like that might fix it, and just to debug, I'll print out the hidden state to make sure that we're still not getting nans. Okay, so we are still getting nans. We are getting zeros in between though, so that is confusing. What that tells me is that it's not the initial input that's causing the issue, but rather the fact that when we feed in the input, we start off with correct zeros, but then we get nans back that are fed back in for more nans, and then it becomes a larger issue.
What we can do, Tammy, is like after like the second recurrence, like just kill the program and see if it's just inputting back nan to like see if that actually is the case.
Is. That's what I've debugged it down to. In the second time step, everything becomes nans. Because the first time step returned a bunch of nans.
Okay, so
I feel like it might be something to do with these extra operations that we're running here. So if I remove the connection from the previous hidden state and the bias, let's see if that fixes anything. No, that does not. So that was not the issue. Although I must say... Okay, so here's actually what we can do. We're going to print out Z, and then we're going to just exit so that we stop at the first time step and just see what it looks like at the first time step. Okay, so in the first time step, Z is fine, so there's no issues with Z at all.
Can we kill it at the, like, print out H and C at the bottom? Oh.
Yeah, so we're going to do, well, not exactly. We're going to print out, like, the individual gates now.
Okay.
See if maybe there's an issue in the slicing logic. Who knows? Because I translated the slicing logic from Swift to Python, I might have missed something in there. Okay, so Z0, Z1 are fine. Now Z2 and Z3. Okay, so those are all fine. There's nothing wrong with the slicing logic, which in a way is not good, because if it was something with slicing logic, then we could pretty easily fix it. But let's continue.
Let's just hope it's not from the next few lines.
Yeah, let's hope. Ooh, okay. So it looks like when we run torch.sigmoid, that's when we start to mess things up. Let's try running f.sigmoid, which is the torch functional thing. So torch functional sigmoid torch NN functional. So import torch.nn.functional as f.
Okay.
And then we do this, and then we do this. This is technically deprecated, but it's possible that there's like a difference between the implementation of those two. What? Oh, well, of course we want to exit. Never mind. It might not have actually been an issue with I. Yeah, no, never mind. I is fine. We can continue to use torch.sigmoid. We forgot to exit. Let's try F. I also think F will be fine, but I'm just doing this in case. And now I'm pretty sure that the issue is actually going to be with C, because that's the most complex operation that we've got so far. So let's see. So we're going to go ahead and print out C. Okay. C is also fine.
So I'm guessing H.
You're right, but just because one too many times I've encountered an issue because I thought something was going to work, I'm still going to test O. Okay, O also is fine. Now
So
let's see
H.
H. If H works, I will be incredibly confused.
Let's see.
H does work, actually. Now, why does H work? We're going to have to figure that out. Okay, so let's just print out TS hidden after this and then exit. So after each time step, we want to print out the hidden state that we got back. That worked. Okay, what about the cell state? Okay, the cell state is also fine. Both the hidden and the cell state are fine, actually. I have a feeling it might be with the fact that I'm storing these tensors in an array without like copying them or something. Maybe if I don't store them in that list, then PyTorch will be happy. So if I print out TS hidden here and exit, if this does not give me nans, then that was the issue, and I just need to create a copy of the tensor. Okay, that didn't give me issues. Now if I do go ahead and actually append to the list, then that also worked. He would think that it would be a good thing that it worked, but it's not. Alright, so what else? Okay, so then where are we calling this next? Well, it shouldn't really matter where we're calling it next, should it? I feel like it might be an issue with the data that we're feeding in somehow, maybe?
Might be. We can output the data and see
It
if
should all
it's
be correct. It
correct.
should be one hot encoded, because I've outputted data before and it does look like the data is correct. And this logic should do purely one hot encoding, like there shouldn't be extra inputs or outputs. So that couldn't be the issue. Let's try and figure this out.
It might be because the tenants are we assuming A to be index 0 or index 1?
We are assuming the individual characters would be the individual characters would be the very last dimension of the array.
Okay.
Oh, okay. Would you look at that? We're getting a different error now. Well, of course, that's because I forgot to revert one of my changes. But Now what this is going to do is it's going to let us see. Let's see. Okay. Oh, well. And I forgot to stack it. Of course we got to do torch shot stack. What I'm also going to do really quickly is I'm going to put an input here, just so that I need to click enter for the next iteration to happen, because I don't want to just like infinitely print out too many. Okay. Now I think I've narrowed it down to where the error is actually occurring. So the first call of a recurrent prediction works perfectly, but the second call doesn't work.
Okay, so I guess we have to print out everything that we assumed before and see what happens.
Yes, but for the second time step.
Yes.
Even though that shouldn't really change anything because the internal state does not change at all.
Okay, let's print out H, and let's also print out C.
Okay.
Yep.
Great.
Let me know when you run it.
I'm running it, and let's see what happens. Okay, so we get all good results for the first one, no nans whatsoever. For the second one, everything is suddenly nan. But we can fix it. We just need to figure out where the error is arising from. So for the first batch, it's fine, yeah?
I think you should sharing your screen on Zoom because I'm unable to see it.
Oh, on Zoom?
Yeah.
I haven't been sharing my screen on Zoom. You've been seeing the code through Atom.
Yes, but I haven't really seen the output.
Oh, yeah, well.
Yeah.
We're
Is
gonna
that
have
possible?
to, I more than likely, but there is a, let me see, give me one moment.
I've been keeping track on Atom, looking, but I'm not really running this locally myself.
Okay, so then in that case, what I'll do is give myself permission to share my screen, make host, that's fine, there we go. So just do that, and there we go.
There we go. Thank you.
Yep. Okay. So, okay, so back to where we were. So H and C are nans. Now, just so I know, I do want to print out inputs. Oh, it is possible that the input's shape is incorrect, that it's not time major, but I doubt that that's the case. Let's see. So I go ahead and, oh, no, run. Okay, so this is the input. Input shape is correct. It's time major, so time steps, batches, samples. And if we click enter, oh, it's working. So the inputs are not nan, which was to be expected, obviously. Why would the inputs be nan? Now, what isn't expected is trying to figure out, what do you call it? The why we're actually getting nans. So to do that, let's print out TS hidden only, and let's actually step through time step by time step.
The terms we might need to copy the list when we pass it on, because I know Python is very annoying with those.
Possibly?
No. So what happens is with Python a lot of times is when you pass array, you might be passing the pointer to it.
Really? I thought Python was exclusively passed by value.
Half the time with Python, for some reason, it just does that for me.
Oh.
I haven't used it for like a lot recently, but I noticed that's one thing that's really annoying with it.
Okay. Well, we'll take a look at that in a second, but the thing is, okay, we'll take a look at that, but for now, the thing that's confusing me is, for the first time step, everything works fine, which is why I'm thinking it's not an issue with the copying of the actual elements. But then the second time step, suddenly things don't work. The reason I think that might be an issue is because, well, let's actually see if I scroll up. Okay, that's fine. Wait a minute, shouldn't the first input's last element be a 1? Oh wait, no, sorry, this is time step major, not batch major, so that wouldn't happen. But regardless, let's try and figure out why this isn't working. So TS hidden, that's returned as nan, which is why in the next time step everything becomes nan. But we want to figure out why it's nan in the first place. So let's go ahead and print out z after the first time step.
And after the second.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is the 12th one. The next one should be our nans. Yep. Okay. So we know that z is immediately nans. And this is at the very first time step too. So therefore, what that tells me is there's something wrong with these IH, HH operations that's making them do that.
Can we also see the inputs as we go to make sure that that's not one of them?
Sure. Just really quickly, a doubt that I have is that adding the bias might be causing some sort of issues.
No. So nan.
Still nan.
So let's also print out the T hidden and T input and see what's going in before becoming nan.
Sure. And Z, another one.
I don't really think we care about T cells at the moment, TS cells.
You're right. Let's not do that. We want to have as little data to deal with as possible.
Yeah.
Okay, let's see. In case anybody has been watching us code and might know why we're experiencing this issue, let us know. Okay, so looks like everything is pretty normal here.
Okay. Let's see what happens when we hit the nan. Okay, we should be getting nan right about now.
Yes.
Okay, so inputs are all. Is that all zeros?
No, they look to be actually pretty normal. The last one ends with a 1, and they're all zeros at the end for padding.
Okay.
Okay,
so it looks like
hidden is all zeros, but then Z suddenly becomes nans.
Yes. So from that logic, if we plus all zeros to it, what exactly is making it into an N? Is it a self H, like self.hh or self.ih?
I do not know.
Actually, no. In this case, both of them would need to be nan because you just hadn't known.
Yeah. See, the thing is, the linear layer is essentially just a wrapper around a matrix multiply, so we shouldn't be encountering any issues.
I'm very curious because how are we returning nan from both inputs and output?
This is the kind of bug that seems like it would be impossible to hit.
Yes.
Because
But you know, everything we hit during the live stream.
yes, of course.
It's just how it is.
Of course.
You can plan for the best demo live, but you're gonna hit some issues.
Well, then again, that's the whole point of the series. We're gonna hit issues. We're gonna show people how we fix them, how we go about fixing them.
Yes. Just like a few hours later. But it's okay.
Well, hopefully we can fix this soon. Unfortunately, we will
Yes,
probably have to
if
hard
we-
stop at 3.
Yeah. So the thing is, if we can get into like a proper IDE, we can probably time step it, like step into the code and see exactly what is happening.
Yeah, you're right. Should I open up IntelliJ?
Yeah. So let's open up IntelliJ.
It's time to
You know I
bring
love
out
my
the-
IntelliJ.
time to bring out the big guns here.
Hey, finally, something that I'm actually gonna be good at. Okay.
Ooh, no, way too much stuff is open right now. Way too much stuff is open right now.
Too much stuff, man.
Is this something that... Okay, this is not confidential. Okay, good. So, let's go ahead and create a new project really quickly, since we don't have much time left.
Python.
Where is Python?
Is
there
there
even-
Python stuff?
Oh, wait, no, sorry, I was using it... Yeah, sorry, not IntelliJ. I use Visual Studio Code for my Python debugging. I forgot.
Oh, okay, sure. Whatever we can do, as long as we can timestamp it. I mean, step into the code.
Okay, so new file, and I'm gonna create a new file called within here.
Can we put in the exact same location since we reference in the path virtually to the file?
Sorry, one sec.
You should really update the path.
Yeah. All right. Okay.
Wait,
So
go back
now-
up.
Yeah.
Go back up. Can we just change open to F?
What?
Line 11. Can you just change that just to F? No, like line 11. Why is it open?
Oh yeah.
It should just be F.
Yeah, that was.
That was so weird. Oh, go back up. You
Forgot.
missed something. No, everything's okay.
Okay, good. So if I run this, in theory, we should get a bunch of stuff that we can debug.
Yeah. Can we also add a breaker?
Well, let's hit that exception first. See the debugger in action, and then. Well, I forgot there
There's
was
no exception to hit.
Yeah, I
Just
forgot.
We have to hit it. Yeah,
I forgot. Okay.
Okay. Are we in the build?
Ooh, sorry, I forgot to run with the debugger.
I haven't used VS Code in a long time.
It's fine. It's really intuitive, kind of.
As intuitive as IntelliJ. I'm sorry, JetBrains is like amazing like debuggers.
Well, okay. So let's see here.
My opinion.
Looks like, of course, for the first 12 we should be okay. So 1,
Yeah.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now this next one should give us nans. Well, so it's 0, but if we break over here, we should get nans inside of z. Yeah.
Yeah.
And the reason for those nans is beyond me.
Okay, let's do this then. Let's go back to all the zeros and let's step into each of the functions and see what happens.
Oh, wait a second. Did we? Never mind. Whatever. What were you saying?
Let's run this again, and as the number 12, let's go into the function directly and see what's being
Yeah,
executed.
sure. Perfect. So stop, rerun, step into the function next time.
Yeah. One everything is 0.
Okay.
Kind of slow, I have to say. Okay.
All right. So 1,
2,
well,
1,
2. Wait, no. 1, 2, 3.
Okay.
4.
Everything will be 0. You can just keep going
Yeah.
until
Just keep
everything's
going
0.
until it's all zeros.
Yeah.
Good idea.
And it should be like right above.
Alright.
Okay, so let's step into it. Is that step over or step in?
This is step
No.
over. This is step
Step
into.
into.
Okay, we've stepped into. Step into again, I would assume.
Yes. Oh, does it not follow the code?
I don't think it is. Which?
Does it
Oh,
really-
look. The linear call is returning a bunch of nans for some reason.
Okay.
Yeah, so it is the linear that's returning the nans. And once again, I do not know why. I feel like
can we
let's
change
just
it
do
back
this.
into
Let's do this. Super simple. Let's go back to having two matrices that we do a matrix multiplication with ourselves. Like this. And then we would do torch matrix multiply the input by the weight. And then similarly here, HH, TS. Okay. Let's try that out. I mean, I don't think that'll fix the issue because linear was literally just a wrapper.
Does it work? That's a question.
Let's see.
Okay, here's all the zeros. Let's step into it.
step into, step in. What? Oh, it worked. What? How did that work?
It worked. Okay, continue.
Hooray! That's amazing. What?
Okay, let's see the next round.
Okay, so let's see here.
You don't have a break.
Oh well, we got nans again, but at least it worked for the second iteration.
So let's see where it's failing. Can we put a index on Z0 and we'll see when Z become on NAND?
Yep.
A little bit better.
We're a step closer. Okay, so it looks like it's fine, it's fine, it's fine.
Okay.
Okay, looks like we're no nans yet. Let's go ahead one more. Looks to be fine.
Go again. Go
We're
again.
fine. We're fine.
It's okay if the TS input always seems to be 0?
Yeah, because if you scroll like ahead far enough, you'll see ones.
Okay. Oh, okay, I see now.
Okay. Everything looks to be normal.
Okay, that's the second round.
Still no nans, which is a good thing. I have a feeling now we're encountering nans somewhere else.
You know what we can do?
What?
Let's do a kind of a dummy way of doing it, but we assume that every round is what, about 12 or 13. Let's just do like a simple if statement, and then once we go inside, we'll just break every like 12 like lap.
Sure.
So we kind of know which round is breaking in.
Yeah. Okay.
And then from there we can like debug more into it.
Okay. Well, one thing that I will say though is that per time step, we're no longer getting nans in this next function here. If you take a look at that.
Oh yeah.
See that? Now if we move our breakpoint somewhere like here, let's see if X is nan at all. No nans. That's a good thing. I feel like we're encountering nans somewhere completely different now, which would probably...
Can we do this? Can we check if we can do the whole training? Like one whole loop route?
You see that? Why are these linear layers so picky?
Which linear layer is this one?
Over here, this one. This one's causing the nans now. I'm relieved that we found the issue, but at the same time, I'm incredibly annoyed at the issue itself.
I feel like what we should do, every time we have a linear layer, just put a little debugger there.
Yeah, we're no longer going to have linear layers after this. We're just going to have weights and biases manually.
Okay.
And then we'll just do...
Let me see if there's any questions.
No, X self H W plus self H2OB. And now I have a good feeling this will work. Without the need for nans everywhere.
So someone posed, I have been staring at a bug for 33 hours now and still not able to come up with a solution. We might be in this for 33 hours.
Who knows? Well, hopefully not. This is a pretty simple example. We should be able to get it pretty quickly. But although there is a completely separate issue now, Optimizer got an empty parameter list, which is not an issue that we should be facing, which I will search up. Let's see. I feel like in PyTorch... Okay, did I mistype an initializer somewhere?
Let me double check code.
I do not think I did. No, I did not. Well, let's continue debugging. PyTorch custom layer parameters. Okay, Looks like when you have a custom parameter, you actually need to tell PyTorch that it is a parameter, which makes a lot of sense now that I think about it, and I wasn't defining any parameters because everything is custom. So that's an issue. But it's pretty simple. You just wrap it around torch.nn.parameter and you feed in your tensor where data is. So let's go ahead and do that.
Let's see if this will fix some of the issues.
I have a feeling it will. We might not even need to call torch.rand because I feel like the parameters might be initialized automatically. We should just be able to call torch.tensor. Let's do that. And then of course we also have to do the same thing like over here. So just
let's hope this is actually the issue and not something else.
I have a feeling it's more than likely the issue. And replace rand with tensor. Okay, let's try this out.
Debugging mode.
Yep.
Oh.
It takes one positional argument, but two were given. I need to pass it the size manually, of course, as a tuple.
But you know there's a lot of places now.
Luckily, not too many. Again, see, this is the thing. This is the first time I'm really coding something this intense in PyTorch, so...
well, this is my first time using PyTorch, and is this also your first time?
Almost. I mean, I've used it for simple stuff before, but never something like this.
So basically, both of our first time using PyTorch.
Essentially.
And something else.
Tensor missing one required positional arguments.
So you need data.
Yeah. So maybe then we just do call torch.rand or tensor.rand. Oh, do I need to remove the size now?
Why don't you
let's
just
see
do
if
that completely?
Yeah, let's just see if torch.rand is tolerant of size. Yes, it is. Okay, I don't need to remove it.
Size
well, yeah, if you only have one, you have to put a comma at the end of the tuple to really make it count as a sequence. Is it running? Is it not? It's not running. Now it is.
Okay.
Okay, we had a breakpoint. Step in. Hooray, no nans.
Okay, continue.
And if we just run it all now.
And then.
Okay. Now the issue is probably not in the actual execution as much as it is in the loss function is my next sort of worry.
Let's do the loss function.
Well, let's first of all debug forward and just make sure that there's no issues with forward. It might be this softmax layer is now getting angry, but let's see. So, okay, softmax is fine right now. Looks good here. Ooh, X is a bunch of nans again.
So you look like you stopped sharing your screen. I mean your webcam on live stream.
Oh yeah, that's because there we go. Okay. Okay, so now I think the issue is that when you wrap any tensor in the parameter and you are actually like what do you call it? When you're tracking the gradients, then you encounter this issue of the not in numbers. Well, let's just see. Let's see if this is an issue that a lot of people face. PyTorch linear layer nans. Huh.
Could it be like the numbers begin are very small?
Maybe, although I doubt that would be the issue because it should shouldn't matter. I mean, matrix multiplying by like 0 doesn't really matter. I mean, I would assume that PyTorch or generally the multiplication would be numerically stable.
PyTorch is what the second release?
Oh, wait. Maybe... I want to make sure my training loop is correct. PyTorch training loop. So, to load the data, you do this. This is pretty classic. Whatever here, that doesn't matter. Loss function is fine. So you calculate, so you set the 0 gradient, you calculate the loss, you go backward, you step. So 0 grad, calculate the loss, step. Why should that cause an issue? If this is actually the issue, I will be angry, but let's see.
I don't think that would be the issue for this.
It's not, thankfully, it's not. Because otherwise I would not have enjoyed coding in PyTorch as much as I do. I thought that might have been it, but it's not. Let's put a breakpoint here too and see if it's arising from the recurrent network or from the thing. Okay, so it is arising from the recurrent network. And within the recurrent network, okay, you know what? I feel like the mistake that I made here was simply in the fact that I decided to write the LSTM cell from scratch. If we comment all this code out, and if I go ahead and search up torch NN LSTM and just figure out how that works, I feel like we might be a lot further ahead than where we are right now.
And then sometimes you feel like using the built-in one costs you more headaches than just making one yourself.
Well, sometimes. I don't think right now is complex enough to be causing more headaches, but...
Yes.
27 to 128, yeah. And... okay, so... outputs... so we want the second tuple, the first value of the second tuple. Okay, so we actually want to get 1, 0 would give us the right output. Okay, in theory, that should be all we need to do.
Maybe add a breaker to it just to double check.
I did put a breakpoint right after it so we can see what's happening. Oh, well, yeah, of course, we need to just call it regularly because it's not a custom cell. Okay, we got output for the first time step, but we were before, too.
Second time step.
Even the built-in recurrent neural network is giving us nans.
I feel like it might be the data.
It might be, but I really doubt that it is.
It might be now. Can we verify that the first one is correct?
Yeah, I verified that. Like the first time step gave us no nans for both the matrix multiplication and the softmax after that.
So there's a second
iteration that's messing it up. And also, it probably isn't the data because the data loader is shuffling the data, so it's not like the first batch is always good and the second batch just happens to be bad data because it's shuffling. It wouldn't always be good, bad.
Yes, that is true.
There is a different framework that I have a lot more experience with that we could use if you'd like.
Is it also RNN or is it different?
No, it's going to be the same architecture, but it's going to be a different programming language.
Swift?
Yes.
Sure.
Let's try that out.
I like Swift more than Python.
So do I. Who doesn't? So, here's the thing. We're not going to completely give up on this. I still want to fix this, and once I figure out what the issue is, I will release a follow-up quick tutorial, like video on YouTube, trying to talk about what went wrong with this PyTorch implementation. But for now, let's just transition over to Swift, because I don't want to spend everybody's time just trying to fix an issue with PyTorch, or not necessarily even with PyTorch. It's probably something that we're doing wrong, but we don't exactly know what it is because there's no way to debug that, at least easily. So
this is also a good learning opportunity that show people that sometimes anything can happen, even for someone that is really knowledgeable and say programming and machine learning like yourself.
Yep. So again, that's the whole point of the series, to show you what happens when we encounter issues like this. All right. So just one last thing I am going to quickly take a look at. Yeah, and in this case, we're keeping everything on CPU too. Like, we're not using any accelerators, so there shouldn't be any issue of like different devices not liking each other's tensors. So that will continue to annoy me for a bit, but we'll get over it eventually.
It happens.
Okay. Well. Oh wait. Never mind. Okay.
No.
I had a different idea of how we could possibly make this work, but I do not want to go down that whole rabbit hole of debugging this. So let's go ahead and not try that. So let's just go ahead and create a new Xcode project, and this of course will be a good learning opportunity for you too, Omer, to learn Swift for TensorFlow stuff too. Okay, so I'm just going to create the new name generator project, and then we'll get into it. So again, I've already explained how this model works, so most of the code that I'm about to write is just like a bunch of boilerplate, relatively at least, because I've already explained a lot about the model. But let's just go ahead and do that. Now, one thing that I will need to do, though, is copy over my LSTM implementation, because obviously we don't want to do that from scratch, and in Swift, LSTMs from scratch are better than the ones that are not necessarily better, but they're more convenient currently than the other one, like the built-in LSTMs. So I'm just going to use that for now. So in Swift, of course, it's not like Python. It's not as Swift does not encourage duck typing, so it does not encourage you to just have a bunch of data and expect that things will work and only break when they start not working. It really enforces safety. Like, it has a very it has an emphasis on safety in the language, and you can see that as I'm typing in this code now. Everything has to be explicitly marked as what it is, the properties that it has, things like that. So for example, as I'm storing the hidden size within this structure, I've got to tell Swift, when you're calculating derivatives, don't calculate a derivative for this variable because we don't care about it. And then I can go ahead and initialize my tensors, pretty much initializing them the same way that we were in PyTorch. Slightly different syntax, but if you know how to program in Python, this should not be too far off from what you're used to. And then just call as function, copy in this other implementation, and we're going to be returning output. So the input to the LSTM is going to be a differentiable structure that takes the time step input, but also takes a state, right? And that's going to have a hidden and a cell, because LSTMs have two kinds of hidden states. And so just want to do that. Okay. So do that and just modify. Okay, so that should work. IHHHB. Okay. And then just, okay, that happens to work. Luckily, all the variable names are the same. And just fix this syntax error here. Okay, so now we've got an LSTM cell, just like that. What? Oh yeah, I forgot. In Swift, in-out operators are not differentiable, so we cannot do plus equals, we have to do plus. At least not yet. They will be differentiable in the future, but not right now. Okay, and because we don't need to modify it, we can keep it as a let. We see
Watch this all give us NAND. At that moment, I give up.
Well, if it is all NANDs, then we know it's a data issue and not a framework issue, right? This is how we verify our code, by writing it in a completely different language and a completely different framework.
Don't worry, we're just playing Swift as an issue this time.
Well, let's see. Okay, so we have RNN, then we have hidden to output, which will just be a floating point dense layer. When we initialize, just say the LSTM input size is this and this. H2O would just be 128 to 27 with an activation of softmax. See, this is so much easier than PyTorch. I will say that while PyTorch, I prefer it to TensorFlow, I do heavily prefer Swift for TensorFlow to PyTorch too. So that's something.
That's just your bias since you loved Swift a lot, and you also do TensorFlow a lot. So.
Well, I don't.
Okay,
I mean,
at least.
Just look at the syntax. It's so much easier to comprehend than Python. Well, I mean, then again, you're right. That's subjective, but still.
Yeah. No, but I do have to say the one main downside of Python, which they all fix in the later versions, is that anything can be anything. At least in the later versions, after 3.6, you can define what the input is and also the output. You at least have a little bit of control.
So I'm just kind of speeding through this implementation here because this is, again, boilerplate stuff. This is the kind of thing you wouldn't need to write in Keras at all. But we're going to do it. So hidden equals, what would it be? It would be tensor.
Have we already processed the data?
Yeah, I'm going to just import it from Python, since you can call Python code in Swift.
Yep. Okay.
Maybe we just want it to be a tensor.
So are we going Swift to, no, we're going Python to read the data and send it to Swift?
Yeah, exactly.
Okay. So we don't have to worry about the slowness of Swift there.
It's not slow. There was one example where we've worked together on a project and it was slow in reading data, and it was because of the bad code that I wrote. It's not a Swift issue.
Are you sure it's not a Swift issue?
I'm very sure it's not a Swift issue.
You went into C to get the performance back up.
Don't worry about it.
Don't worry, there are some data that I work with, like XML, and I have to say one thing is so slow to read. Like the rotation and my language I use a lot of Golang, like Go, is hella slow. It was easier just to convert into a JSON, and then you can't read the JSON.
Yeah, I mean,
we're talking like 4 to 5x.
XML is just generally complex to read. It's not intuitive at all.
No, it's not really that. If you actually look it up why it's so slow, everyone's just complaining that the implementation, it was just like, not the greatest. Because if you compare it to like the Java implementation, it was super slow.
I see. Wait, so what we would want to do...
Let me check if there's any questions in the chat.
RNN.recurrent prediction on the input.
Someone messaged, honestly, this will be easier in TensorFlow and Keras.
I don't deny that. It genuinely would be, but...
Yes, I think it would have been too.
Yeah, you're right.
Since everything is technically set size, which is one of the reasons why PyTorch is used, since this input size doesn't really matter. You can make it as big as you want or as small as you need it. While in TensorFlow, everything just status, like they have to be a set size to input.
Well, Swift for TensorFlow it doesn't need to be.
Oh, that's good.
It's pretty dynamic. Of course, it's going to be faster if you don't just feed it different shapes all the time, because then XLA compilation will help you out. But it's not going to be slower by any means. Okay, you know what? There.
You know what we should do? After we actually implement this in Swift, might as well just make a iOS app just for fun.
Thing is, Swift for TensorFlow doesn't compile on iOS right now.
Oh, it doesn't yet?
No, the iOS SDK is different, and Swift for TensorFlow only targets the Mac OS and Linux SDKs.
Is there any update when Google, I think it is, working on it?
What you could do right now is you could export your weights to like a NumPy file, and then you could load them into CoreML, but that's essentially the only way to do it right now.
No.
Okay, so I'm just going to verify that we're not getting nans again, because if we are, then we will continue this live stream later. But if we are not, then we will be happy. So let's just say we have something representative of what our data would be like, and we want to print out that shape. Let's see here.
Okay, so someone is asking, can you make a video on BERT?
On BERT? Absolutely.
Yes. That could be the next project.
That would actually be really interesting. Next week's live stream will be on BERT and natural language processing.
Why not do some WAPERT on that as well?
Oh yeah, we'll talk about with BERT derivatives too.
Okay, I'm more interested into that.
Let's do that next time. For now, though, you gotta finish
Let's
these
get this to
hands.
work.
Alright, so now let's just do this. This is essentially a no-op, like just mapping to the input, but whatever. No nans. Thank God.
But what do you input?
Random data.
Okay.
Okay. So that relieves me a lot.
So let's train it now. Let's see what happens.
Now let's actually feed in real data, yeah. So what I'm going to do is I'm actually going to copy your data pre-processing code, pre-process it, save it to a NumPy file, and then load that NumPy file in Swift.
Yeah, let's do that.
So I'm going to save it into preprocess omer.py, and then just call load data and feed that into X and Y. We're kind of going over our time budget, but that doesn't matter. Okay, and then just import NumPy as np import.
So someone asked something interesting. I don't know if this is really like something we really need to question here is, how many days would it take to learn JavaScript from scratch? I've never done JavaScript, so I cannot answer that. What would you tell me?
See, JavaScript is a simple language, but I would say that there's a difference between learning JavaScript and learning how to code in general, right? Because when you learn how to code, you're not learning a specific language, right?
Yeah, that's true.
You're learning the logic. And that logic takes a pretty long time to gain experience with. Learning the syntax of JavaScript should only take you like, you know, a couple of days or a week or two or something of that sort.
The thing is, we have to look, is it natively JavaScript, or we're looking at the other framework like Node.js, which is a little bit different, but again, same syntax.
Mm-hmm.
I think you're right, maybe about a couple of, if you really know how to program already, then you can pick up any other languages within a day, usually.
Yeah. You are right. I agree with
That's
that.
usually how long it takes me to learn a new language. I'm not sure about you. Well, not like I'm an expert, but like be able to do something useful.
It's weird because when it comes to like just learning a language, you can usually, even if you've never coded in the language before, but you know how to program, you can generally make do with just searching up Stack Overflow and figuring out how to do things, right?
Funny thing is, that's how I learned Go. Just
Yeah.
Stack Overflow.
Yes, of course.
No, because the thing is, how I always look at it is, when you grade, you know exactly the logic in your head. Now we have to just translate that into that language. So if you're gonna do a loop for something, then you know that's gonna exist in, say, something like Go, Swift, Python, Java, C++, C, because they're all loop operation.
Exactly.
Now, if you go into other languages like functional languages, which might not actually have loops, or even recursive languages, then you kind of have to play around with it and see how to really get to work with that concept. So the one thing that I have learned a lot is that you shouldn't really always look at one way to be correct. There might be another way that might be more efficient or even cleaner.
Mm-hmm. I agree.
And it all depends on the language if they enable you to do it or not.
Yeah. Okay, so I'm just going to quickly implement that loss function that we were talking about. So y hat times y dot sum squeezing the last axis, which would be axis 2, and then literally just feed this all into log, negate it, find the mean.
Okay, so after this test, there's, I think, two more questions. We can,
we'll get to that in a moment.
yeah, afterwards.
Okay, so we have the loss function. I'll just make sure it's marked as differentiable so Swift actually can calculate gradients properly. And I'm just going to guesstimate the number of batches for now. So
Fine. Just quickly.
I think there's actually like 200 batches. 210, probably. Yeah, 210. So then we calculate the batch x, which would be the slice of the inputs from 0, 0, 0, which the first one would actually be batch index minus 1 times 32, which will be our batch size. Then the upper bounds will just be batch index times 32, 1227. And then something similar for batch y, like so. I think that should work. Although what I would want to do is transpose it such that we have it in time major format like that. That way we can get the loss and the gradients with respect to the model by doing TensorFlow dot gradient at model and then giving it a closure in which we actually call the operations that we want to calculate the derivative with respect to. So we do loss y hat model batch x y batch y, and then, well, maybe we'll call this cross entropy loss so that we don't duplicate symbol names. And then we can do losses.append loss.scalar, kind of like loss.item in PyTorch. And then we can do optimizer.update the model along the gradients. And then just print out the average loss, like this. Okay, let's build. Well, of course, we gotta call model. Huh. Oh, I have to say value with gradient. Okay, so we want to convert this array back to a tensor before we return it, because otherwise we're going to have to deal with a tensor and an array, and it's going to be weird. Okay. In theory, our training loop should be done. So let's see. Okay, so we don't have any questions currently. Let's go ahead and run this code and just see. By the way, one thing before we run the code, I'm going to tell Swift to go onto speed optimizations so that we can get this to run as fast as possible. Oh, we have to give it explicit path. By the way, one thing that I do want to point out is the interoperability between Python and Swift. People are saying that the audio is echoing, unfortunately.
Yeah, so I'm trying to figure that out. I do hear a low echo on the video, but I don't know what's coming from because I can hear you crisp from my headphones.
I will try putting on my headphones as well. Give me a moment.
Yeah, it might be because of that.
I'll try.
Once you're done that, let me go back to the video and see if I can hear it.
Test. Okay, so you should be able to hear me better. I'm also gonna. Okay, Omer, can you say something?
1 sec.
All right, I can hear you, and hopefully people can hear me now too.
Yeah, so it seemed like it was actually anchoring my voice when you're talking.
Hey, Omer, look at this. Oh my God! I figured out what the issue was.
Nan?
Oh yeah. I think I. Oh my God. If
People are saying it's from me.
it was not from you, I had written this line of code. Oh God.
No. People
It
saying
was
the echo is from me. It's actually because it's coming from your speaker and going back into the mic.
Okay, just a second. This issue is just absolutely incredible. Oh my God.
What happened?
It just really goes to show that you should be processing your data correctly, and you should know that you are processing your data correctly.
I did tell you the data was incorrect.
Remember how I said in the very beginning of today's live stream that one extreme point of caution is that if we pad the output with all zeros, we will get nans?
Yeah.
Because softmax cannot fundamentally work with all zeros? Well, that's the issue. And the reason PyTorch was only encountering that issue when we would do it through the parameters, because PyTorch was only ever PyTorch was only ever calculating gradients, which would be going through the loss function, if we were using that. If we were going through that. Sorry, because only if it were actually parameters, not if it were just a raw tensor. So we have to append the padding with blanks, Omer. That was the issue.
Blanks. Oh no, go back.
I'll do it here.
No, because blank is defined as.
No, blank. The last one is a 1 at least. See?
Yes. Is that what we care about?
Yes.
Okay.
Because if it's all zeros, then it's just going to nan out because it's not supposed to be all zeros. There should be at least a label.
Okay. So at the very end,
Now,
it should be the
if we run either our Swift or our PyTorch code,
let's do one and see what happens.
yeah, let's run Swift because we've already wrote all of it. Oh my God. That was it.
Oh, so let's do this in Python and see what happens.
Yeah, I guess so. And look, our loss value is decreasing.
Oh, nice.
Oh my God.
Slap this on a few GPUs and let it work.
We don't need GPUs for this.
I know, there's such a small data set.
Yeah. Okay. Now that a few, actually many, minutes of painful debugging are over, let's actually go ahead and try this out. Did we modify something that we shouldn't have modified in the debugging process? I don't think we did. Let's see.
No, should be fine. We might be able to just go back to our custom parameters and stuff.
Yeah, we actually probably could.
But does it really matter?
It doesn't matter at all.
Sounds to work. Yeah, maybe we shouldn't be printing out the size constantly, but it's fine.
No, it's only the first time for the whole data.
Oh, okay.
Hooray!
That's that's kind of bad.
It
How is
is
it 68% started and the other one is like 9?
probably because the parameter initialization for PyTorch is different.
Okay. Oh yeah, I
So
forgot. One is TensorFlow, and one is PyTorch.
yeah.
Yep. How many batches are we do? I mean, epochs are we doing?
Oh, wait a sec. We were going to do 10 epochs. Oh my god, each epoch is way faster in PyTorch. I mean, of course, because Swift for TensorFlow is currently doing eager execution.
Okay, let's do much higher. Let's do
The
like
thing that
100.
I'm not really getting, though, is why is Swift giving us 2.11 and why is PyTorch giving us 68?
Are they exactly the same launch function?
They should be, yes.
Can we compare the two side by side, please?
Yeah.
Double checking them.
We don't want all this garbage. Okay, so
Okay,
this is the loss function here. This is the loss function here.
Okay, are we taking the negative log?
I feel like we might be calculating softmax on the wrong dimension. I'm not. I feel like I'm visualizing the softmax incorrectly in terms of like which dimension it should be run on.
We'll see.
That was definitely not it.
Some to be worse. Can we see the name model generation on TensorFlow? See what the difference there is?
The what?
When we initialize in the model, is there any difference?
I mean, the only difference. No, it's actually the exact same. We're using random uniform here and random uniform here too. You know what? Let's just do this. For now, for the sake of simplicity, and since we're already a lot over our time budget for today's live stream, let's just run this in Swift for TensorFlow, get a good model, generate some names, and we'll do PyTorch later.
Sure. The next live stream, we can quickly give them an update on what happened, and then let's go to the next one.
And then we can talk about BERT. Okay, so it looks like our loss is decreasing. That's amazing. However, it's not going to really be of much use if our model is discarded after the training. So we have to do something with it. So how about we go ahead and generate a perfect name? Then we'll go ahead and write the code for generating like actual names. And then while it trains, we'll take a break. Like we'll go off while it trains, and we'll keep it on the training. And right as it's done, we'll be back.
Yeah.
So for now, let's go ahead and implement the perfect name generator, which shouldn't be too hard. We would need to make a small modification to this model over here, which would be no derivative previous hidden state, which I'm just going to say is TensorFloat, and previous cell state, as well as a mutating function called reset state, which should just say previous hidden is a new tensor, random uniform 128, so a batch size of 1 and a hidden size of 128. And then do the same thing for cell over here. And then I'm going to have another mutating function called step, which will just take the input at a time step and return the input for that time step. So we would just do RNN on init, input being input and state being initialization of hidden, previous hidden, cell being previous cell, and then just return H2O of X. I think that should handle it for us. Dot hidden. Of course, we would want to do previous hidden equals x dot hidden, and previous cell is x dot cell. Okay, go ahead and build this. Build failed. Why exactly? Does anybody know? Oh god, please don't be a Swift or TensorFlow internal error. Because this is pretty new stuff. I mean, there's sometimes like internal errors within the compiler. Never mind, thankfully that's not the case. All we need to do is, I don't think I can actually call that function until I initialize, yeah. So I have to copy and paste this code. It built, nice. Now all we would need to do, I believe, is implement, so the perfect name generator would be simple. It would say previous, or characters, right? Let's see, int, and then we could do while true, if while true and characters.count less than 11, so we're going to stop the network if it tries to generate a name longer than 11 characters. So if, or we'll say model prediction equals model dot step, and the input would be, well, we're going to start off with blank, so previous input, tensor float zeros, 127, previous input 0, 26 equals 1, so that would be a blank label, so then it would just say previous input. And then model prediction 0 dot argmax, I believe. We could just say characters dot append model prediction. Of course, we would need to convert this to an integer, though. And then previous input is equal to, well, we would need to convert it back to a one-hot representation. So then we would need to create a new tensor and just say previous input is equal to those zeros again. And then from there, we could say previous input characters.last equals a 1. And then print out the characters. And then we can figure out what those characters represent later, but for now, at least we'll have the perfect name generator. Now, just because... Yeah?
Go.
Now, just because I don't want it to, like, fail, I'm just gonna do, like, 2 epochs and then check that out. We don't want to train.
I was gonna tell you, maybe we should make 2, like we save the weights and we'll load back to weights so we can do the test. So we don't spend 2 hours trying to, like, train it and then get 1 test.
Well, not literally 2 hours, but, like...
Let's see. Well, two epochs doesn't take that long. We can do this on video.
We should get a perfect name after this.
Ooh.
Oh, wait, I forgot. If characters.last equals 26, then we have to break. Yeah, see? Oh, wait, one more thing. There. Okay, so we shouldn't get any exceptions, but we should get really bad output. Maybe even just a single time step. But as long as we're getting something, I'm fine.
Watch it just print your name out. We got 26. Oh. We got blank.
Alright, that's fine then. I don't care. At least we're getting something. What?
How is that fine?
Because we're only doing 2 epochs. The model's probably just overfitting to always return blank.
Okay, yeah, can we do a little bit more epochs just for the sake of it?
4 epochs. 4 epochs.
It's like we create a model to determine if this is a hot dog or not a hot dog, and then we just always assume it's not a hot dog. What is this? Okay. Doesn't look like
I,
it's been any
I
better.
know that sometimes it just needs a little while to find like a good point in the gradient space, and then after that it goes down really quickly, like it starts to converge.
26. Nice.
Well, honestly, I feel like we're good enough to go ahead and train.
Yeah, let's just train for like a good amount and see what happens.
30.
Let's train it 30. And then we can pause the live stream and come back in what, 10 minutes?
Yeah, 10 minutes, or right as it's done. So
Yeah.
this will probably take less than 10 minutes. Within less than 10 minutes, we will be back. All right, let's just let the first epoch go, and then we'll pause the live stream.
Yes.
All right, so we're going to pause the live stream. We'll be back in less than 10 minutes, right as the model is done training. All right, so we are back. Unfortunately, it seems like we're encountering another issue, and that is that we are only getting a blank label as output. We don't seem to be getting any other output in the first place, which is perplexing to me, but we're going to fix it. Let's try and figure out why we're getting this issue. So the output of the model seems to be So the previous input, of course, we're feeding in a blank. That makes a lot of sense. The output then seems to just be a blank label. And that blank label is telling us that, hey, we're done. There are a couple of ways we could probably work around this issue. One of them would be to separate the blank label from the end label, which I think is the easier way to go about it. The other way to go about it is to try and figure out exactly what's wrong with the data that or the way that we're currently doing it. I would personally rather go with... How would we deal with a blank token then, though? Would we just ignore all the blank tokens?
We can do that, because, well, to be fair,
No, actually, we
have a
couldn't do
spare.
that. We couldn't just ignore the blank tokens, though. And the reason I say that is because, in that case, if we were to ignore all the blank tokens, then we would just be feeding the same input in over and over again. We would keep getting the same blank output, and we would keep having to
Can we
ignore
not
it.
do this?
What?
Let's separate the blank from the end, and then at the very, like, the end character, let's just put everything as the end.
Put everything
So
as
in the
end.
input, we only have one end character and a bunch of zeros.
Yeah.
Change all the zeros to just the end character.
But there's only one time step in the input right now, though, and that is nothing. Or, you know what? Let's actually do this. Let's, for now, I'm going to make a small change, actually. Give me one sec. And what I'm going to do is I'm going to prime the model with some input and see if the priming changes anything. So... let's just do var a, and then so what we could probably do then would be... No, but then that would really increase the logical complexity of this. Honestly, this should work. Let's just Control-Z this. That would be a whole separate rabbit hole we would be going down in terms of priming. Okay. Again, the way that we could fix this, which would be pretty simple, would be to implement gradient masking. Now, whether or not we want to implement gradient masking is, let's see. How does Keras do it?
Doesn't seem to be too
Oh,
bad.
you know what? You know what? Let's just do this. Since Swift for TensorFlow does eager execution, right? Because Swift for TensorFlow does eager execution, there's actually a pretty simple way to do this. A way that... Okay, I'll just show you. So, what we could do would be differentiable function call and calculate loss. Feed it some input, right? And then what we could do... For the time steps that are zeros, just zero out the gradient. Multiply them by 0. So that would have to be a mask. Okay, I think I got it. We actually wouldn't even need to do this weird workaround. All we would need to do is our loss function would need to take a mask. And we would need to multiply by the mask. Well, after the sum. So then what that would do is this. We would take the index of the most likely output, we would calculate its probability, actually, we would be doing the multiplication after the log calculation. So, we get the negative log probability, then we multiply by the mask to zero out all the time steps that are responsible for just padding, then we calculate the mean value. Make sense?
Yes.
Okay. Now how do we calculate where the mask has to go is in Python. So, that means we would also need to return a mask. So we would have to do the first name length plus 1 time steps are fine. The rest have to be discarded. So we can do mask is equal to 1 times length of name,
Plus 1.
and then while len mask not equal to pad length mask dot append 0. And then we can just return np array mask. And of course we have to deal with that here too.
Do we care about the very first index?
Yes.
Okay, so don't we need to also make sure that, because everything will be offset by 1, I believe, because we inserted a 0 in the very beginning of the input.
Yeah, but that's fine because that's supposed to be there. It's a blank input, but there is a valid output.
Okay. And then we only care about the up to the length or up to the next one afterwards?
The next one afterwards.
So
because we want to predict that, oh, we're ending now.
Yeah, so
I did that. Oh
we
yeah,
might
len
need
name
to
plus
max
1.
plus 1. Yeah.
Yeah.
That's what I was gonna mention earlier.
Good idea. Okay, so then we just return xy mask, and then we can do xy mask, and then np.save mask.
Yep. Let's see how this works.
Okay, now let's mentally visualize the shape. It would be samples, and then 12.
Mm-hmm.
And the input that we're feeding in should be 3212, I think. So the input that we're feeding in would be 32 times let's just do this. Let's go, since I'm unable to properly visualize this, let's just go ahead and print out this shape. Again, this is not efficient code whatsoever. You should not write this code this way. But I'm going to, for the sake of debugging.
Are you okay? Wait, why are you commenting? Okay. It looked like everything was just coming out.
Yeah, because multi-line.
Like, can you not print out the negative of the log?
It's because it's thinking I want to print out the negative of the shape.
Okay, this is a negative
so
shape.
384, so... Oh, thank God. Okay, so it's the right shape. All I would need to do is flatten it, which is fine with me. Okay, so just do that.
But the max are we creating, is it that size?
Yes, it is.
Okay.
Because 384 divided by batch size is 12, which is the number of time steps.
Okay.
And then I'm just going to flatten this real quick. Load in the mask. And this should instantly drop our loss value too, because we're not calculating as much of a high loss.
Yep.
All right, let's try this out. I have a feeling this might work, but I also have a feeling like it was too easy of a fix.
We might get 1 or 2 characters.
Who
Hopefully.
knows? And of course, I forgot to run the Python file.
Okay.
All right.
That was an easy fix. Wait, why do we need to build it again?
We don't. We just
Oh.
run. It uses the cache build.
Sorry, I'm just so used to like
Oh,
other.
hey, a much lower loss value. So we are masking. Now, hopefully the gradients aren't flowing, and I know how the gradients flow, hopefully.
Going slow, but going down. It's about the same as before.
Yeah.
Ish.
Well, I mean, in terms of performance, it's the same as before, but, like, the loss value is instantly a lot lower.
And okay, it went down.
So now
Very
it
slight.
shouldn't at least overfit to, like... Okay,
Hey, there
now
we
it's
go. 1, 1,
overfitting to
1, 1, 1.
something else, but it is at least giving
We
us
zoomed in.
something.
Can we now print out the last step?
What?
Can we train this for like another like 10 rounds or
Yeah,
30 rounds
let's
and see
do
what
that.
happens?
Let's do that. Yeah, because this looks like pretty much the exact same thing over and over again.
Yes. Well, I learned B is a good character.
It really likes the letter B.
I guess not supposed to be a B.
It is.
Yeah.
It is.
So we already
Okay.
know who the favorite what the favorite character of this program is. It's a B.
Well, that's with a few training steps. If we increase the number of training steps, it'll probably change.
You hoping for a T, and I'm hoping for a B. We'll see.
Let's see. Now the real question is, are you hoping for a B or an O?
Okay, both are my name. I'm actually hoping for OK. Okay. And you hoping for a T B? Let's be honest.
Okay, while this is running, it's a good time to double check logic and just make sure everything's written the way it's supposed to be written. Which I think it is. I don't see any logical errors, at least.
I feel like the zoom maxing really make me look like I'm have green on my whole face.
Oh yeah, kind of.
It's like
It's not really that noticeable though.
it could just be the light.
Probably is.
Yeah, it could be just be light. Let's see if there's any questions. Nope.
It doesn't seem like our loss value is decreasing very much.
It looked like it just got stuck. It is going down something, but
Not a lot. Not a lot at all.
no. We will see what happens because maybe eventually it will find something that's good and it will drop.
That's possible.
Maybe just stuck in a very smooth, small decrease of a slope.
Possibly.
Why did it end?
It's still overfitting to 1. You know what I want to do? I actually want to load in the input data and just verify that we're actually encoding the data properly. Yeah, I want to do that. Let's do that. So we can probably just do that in the REPL. So load in X. It looks like it's correct.
A blank
Now
character at
just
the beginning and then
A, B, C, D, E, F, G, H, I. Okay. So then A, 1, 2, negative 1, 2, GA 1 to negative.
What are we trying to do? Accomplish?
Just trying to make sure that the data is actually like correct. Okay, so then dot bar max axis 1. Okay, and then GX 4X and okay.
Wait, what?
It does not look like we are processing this data properly.
Wait, what?
Omer, I think you might have messed up with the
Are we sure I messed up?
you probably messed up with this portion over here.
No, but you
My
can try that. That's technical work.
well, let's see if it works, Omer.
So let's put any character there. So let's put A or B. Yeah, that should equal
Okay,
2.
B works. H. Oh wait, it's shifted ahead by 1.
Yes, isn't that what we want?
No, we want to do -1. Omer.
Okay. Just put it back into a 0.
There we go.
Wait, I did ask you in the beginning. Do you want the first one to be 0 or 1?
Well,
Okay, at least we found this.
yeah.
Okay, can we try this again?
Yeah.
Okay, let's load in the data and see if we can get something that's readable.
Okay. Let's hope. Okay, so a slightly lower loss than before initially. Hopefully it actually goes down. Oh, it's starting to go down a little faster than before.
Yeah, but they got stuck at 1.62, I believe, last time.
Did it?
I think. I don't remember exactly.
Well, I have a feeling that now that we've fixed this issue, we'll be at least slightly better.
So on the channel is what printing is the loss? Yes, it is the loss.
Yeah.
So we're trying to see like what's the loss at the moment and trying to generate a name. We're having issues. We're just generating, I'm guessing, A, apparently, because A is 1.
I do not know why the model was overfitting to always print out A.
You're happy it wasn't a B. And I don't see any other questions related to that.
Yeah, looks like we've stagnated again.
Okay, we'll see. Watch it just print out 0 now. I feel like just assume it will be a bunch of A's and then that's it. But again, we're not really training that long, so it could be, it might just need a bit more
Okay,
time.
if this still doesn't work,
See?
yeah, now it's overfitting to 0. Okay, last thing we're going to try out here. I want to take a look at this data and see just why it's so terrible.
This one should be greeting, I believe.
What's the first word?
Greeting, I think. Once you print it out, you'll see it. Okay, I'm back.
Okay.
6-4. Let's see what happens. Oh my god, you cannot code. E, yeah.
Look,
so
of course. Okay, so George, I'd assume, or something of that
George,
sort?
I think. Yeah.
Oops, sorry. Wait, what? Oh, yeah. Yeah, George. Okay, so your code isn't still causing issues. Well, in that case, maybe that wasn't. Maybe then we don't actually need a mask. Let's see what happens if we just ignore the mask. Maybe the mask itself is causing issues somehow.
I don't think that will be the issue.
It's almost definitely not, but I would like to try. And in the meanwhile, while that runs, I do want to check out that logic one more time and just really get accustomed to it, because so we're inserting a blank, then we're inserting zero padding here. Whereas here, we just consecutively insert blanks, which makes sense. Here, however, we are appending zeros, but we're not using the mask, so it doesn't matter. Well, we're not using it anymore, at least. Oh, God. Okay. Now it looks like we're stuck at 2.09. I think you're muted.
Yeah, I was muted. My bad. That's not too bad. We'll see what happens. Watch it just print out something else other than all zeros.
Well, hopefully. And now we're back to predicting 26. Isn't that just great? Okay. So we feed in a blank, which makes us predict a value, and the final value predicts a blank, and then a bunch of zero padding, which is blanks. I do not see why that shouldn't work, honestly. We even have a mask to help it. Why does it overfit to A? Are there just lots of A's in the dataset? There's no way that's the issue. You're muted, by the way, just so you know.
Yeah, I know. I was messaging someone else.
Okay.
Okay. Let me see.
I'm wondering if we should rewrite the data processing logic in Swift.
You know what? Might as well. Let's see what happens.
All right.
The only thing we prove is that it might be easier to do everything in one language than two.
Yeah. All right. We'll be back in just a moment. Okay, so after a lot of thought, we decided to rewrite the Python implementation in Swift. Now, technically, this is the exact same implementation, but there's a chance that importing, we realized a logical error and we fixed it. So let's see if we ended up doing that. So this is the same thing as Python essentially, but we're not calculating the mask. So what I'm going to do is comment out this and this and this. No, this and
And the
this,
one below.
and just do let x y equals one hot characters in load data. And then also we no longer require a mask. If we think it's necessary, we'll add it back in. And let's see. Who knows? Maybe we missed something somewhere that caused this issue. But I somehow doubt it. But let's see. Do we need to return manually? Yeah. Alright, let's see if this works. Alright. So it looks like we're basically back at where we were with the loss. Oh my god, what?
That was a nice
How?
jump.
How did
What
that
happened?
happen? It's literally the exact same data. What could we have possibly done
No, there we
differently?
go. It got stuck.
Well,
Ish.
we can hope that it's not stuck.
Let's hope. How many epochs are we doing on this one?
10.
10? Okay. Let's see if it hit below.
I really hope it hits at least 1.
Watch at the very last epoch, it just dropped down to the 1.9. Ooh, that's such a
Truly
small
hope so.
difference. Alright, look like we're going 0.00003 at a time now.
0.0001 change in loss. Essentially nothing.
Yep.
What I feel like we should do is make it so that we only choose the blank output if it's greater than 0.5. Otherwise, zero it out and choose the next greatest value. But then again, it doesn't fix the fact that we have such a high loss.
Yeah, what was the output again? Just all zeros again?
Well, yeah, just like a
Oh,
single
blank.
and blank label.
I feel like
Essentially
this isn't
nothing. It's
worse
saying
now.
it's saying it just doesn't want to output anything.
I feel like maybe if you went back to Python and just implement the last bit, it somehow
Yeah, I feel
magically
like
worked.
we should actually go back to Python.
And somehow it magically worked. Can we just implement the last bit in
Wait a
Python?
minute. Wait a minute. I think I might know what's wrong. I feel like the shapes are messed up at the moment. That we're not feeding it the right shape.
That might be the case.
Maybe. Then again, the thing that confuses me is to print inputs.shape. After this, what we're going to do is, if we simply cannot get Swift to work, we'll go back to PyTorch, see if we can get something to work there. If not, then we will come back next week, and by then, hopefully we will have fixed this. Okay, so it looks like we have the right shape here, which is perplexing to me. I mean, I understand why we have the right shape, it's just weird that we do. Let's see here. See, we're transposing it, and that's fine, which means that we have time major data, and that we can loop through it and get the outputs. And in terms, it is always possible. Maybe that's the issue.
Look, everything's gonna be an issue.
Okay. I have a feeling this is gonna work now. I'm pretty confident this will work.
I lost confidence a while ago when nothing makes sense.
I see someone said, Ion's awesome facts, a lot of this code is from the TensorFlow site. Well, we've written all of this from scratch. Oh my god, look at that. What did I tell you? What did I tell you?
It doesn't mean anything. You know what? That's not a bad job right there.
Yeah, but actually, to get back to Ion's question, we are writing all of this code from scratch. This is not being copied from anywhere. This is all being written from scratch, live. So yeah, you shouldn't find this code anywhere else. If you do, let us know, because it would be interesting to see if we've happened to written the same code that somebody else has written. So.
And Swift. Keep this in mind.
Yes, exactly. All right. Okay, so you know what the issue was?
What?
We were transposing our input data to be time major from batch major, but then when we were returning it, we were returning time major, whereas we should have transposed it back to batch major so it works.
Let's see.
Look at that loss jump, man.
It is a loss.
Look at that loss
It is the best loss so far, but let's see what happened.
Yeah.
That was actually a nice jump, that last one.
Let's see what the perfect name is according to this model.
It's going to be BK. Let's see. And 26. Of course it's 26. But, well, actually, no, it didn't even get that bad because...
Okay, you know what I want to do now?
Train it for a long time.
Now, I want to use the mask. Again. Because now, we're actually training the way we're supposed to train, and I feel like the mask can help us out.
One moment.
What's wrong here? This is weird. Oh, okay. Well, I need to import NumPy, of course. Okay, let's see if we can get the mask to work now. Last try, okay.
Well,
I'm not getting my hopes up with the loss value right now because we're using the mask and it just instantly makes everything a lot better because we're literally removing values from the loss calculation.
Oh, okay. I forgot about we do the mask right now. I didn't see that. I was looking at something else. Let's see if it worked better or not. You know, I really love this zoom effects because it looked like I lost an arm. It's like a whole side just disappeared.
Yeah, machine learning isn't foolproof.
Yeah, I think they need to like license up the Google one because they have a good like image process, especially when it comes to
Do
blur.
they? Oh, like the Google Pixel portrait mode type thing?
Yeah,
Yeah.
one camera blur, just using mostly machine learning.
The iPhone SE can do that now as well.
Yes, but all the later iPhone they use the two different cameras for the focus point and then
Yeah,
find the
but that would
distance
give you a
based off
better
that.
result though, because then you'd have depth info.
Yes, depth info is always the best.
Okay, so I'm pretty sure it's still gonna overfit to like a single character, just because
No, it's
you
gonna
know
overfit to is 26. I'm betting. I'm putting a bet on 26.
I'm not putting a bet on 26.
26. So let's watch.
How did you know that?
Look, I see the future. Only if I can.
All right.
Only if I was that lucky.
So what I do want to do is print out really quickly um, before we do any of this reshaping nonsense. Print out this shape, print out this shape, and then after this, we'll do the rest of it later because we don't want to have a many hour long live stream. Yeah, see, the shape is the exact same. And then we literally reshape them to the same shape and then calculate the loss.
Mm-hmm.
Hmm.
I feel like this is why you should never ever code live.
But
Because
then again,
everything
I'm sure it's pretty insightful for people to see the debugging process too.
it is true. Because a lot of people just assume that there's like no like everything will just naturally work without
Yeah,
any
and
like issue.
now you can see all the nitty gritty details.
Yes.
Like literally, I mean, you can start to see a single YouTube tutorial on this stuff takes a pretty long time to create, even because just getting all the little pieces to work together is within itself a pretty large challenge.
Yes. Especially once you go into like multiple systems and doing stuff on those, that's gonna be
Yeah,
like a pain.
things just
Set
get
up everything
things get very complex very fast.
very fast.
Okay, so here's what I'm going to place my bets on for now is that we just um, pretend that or actually one sec. Okay, so actually I'll just remove the mask. It's pretty useless. Um, we're just gonna train without the mask, and we're gonna do it for more epochs. So let's just do like 30 epochs, and just see what happens. Um, yeah, I guess let's just see. Does it compile properly?
Okay,
Yep.
let's see if it worked. You know what we should do? If
What?
this doesn't work, let's just train it for like maybe 100, 200 epochs.
Yeah.
And then if it works in the next week, we can just show that it just took a super long time just to learn something as simple as this.
Yeah. All right. That makes sense to me.
Okay, it could generally mean that we haven't trained enough.
Yeah, probably.
Oh, our implementation is very bad. We never know.
Potentially.
Yes.
All of this code will be available on GitHub, by the way, so if anybody wants to take a look at our logic and tell us what we did wrong, then that would be greatly appreciated. All right, any interesting questions you see, or should we take a break until this is done training?
Let's take a break until this is done training. I do need to grab some water.
All right, sounds good. We'll be back, everybody. again, within 5 to 10 minutes. Okay, so we've been just diving through this code trying to figure out what has gone wrong. And we don't exactly know, but one thing I'm going to try now is implementing in that softmax temperature thing I was talking about. So basically, it's going to be stochastic now, and we're going to be getting random names every time. We're going to generate like 5 random names. So let's try it out and see what happens. So essentially what I want to do is just have a new function. And by the way, we re-architected this code a little bit. So like, for example, I moved the loss function directly into this closure, stuff like that. Okay, let's see. So let's create a function called random with probabilities. And let's just make it take an array of floats and return an array of floats as well. Or actually, no, just return the index at which it stopped. And let's create a threshold constant, which will be a floating point random in between 0 and 1. And then let's go ahead and just say current max is 0, and then for I in probabilities, current max plus equals I, and then probably enumerate this and just say I index an I, and then if current max reaches that threshold, then just return the I index. Otherwise, we just want to return, or then we just want to throw a fatal error because we should never reach that point. Then I've already gone ahead and implemented softmax with a temperature of 0.5. And once we've reached that, I want to go ahead and get scalars, so multiple scalar values, and then feed this into random with probabilities so that works. And this should be a float because, of course, Swift is not like Python, luckily. So then we just generate, like, I don't know, 20 random names. You really can't have too many. Let's go ahead and try that out. One more thing that we did is just so that we actually know when it hits the maximum length, we moved this check outside of the while loop and into an if statement. So now we know like, when it actually hits the maximum length. That means that the model didn't stop in time. Okay, so it looks like we need this to be an int instead of an int32. I don't think that should cause any issues. Okay, let's see what happens. How many epochs are we training for? 30. I guess that's fine. Let's see if it works. 30 epochs. Let's go. What do you think, Omer? What's going to happen now?
I feel like going back to Python and just doing this on GPUs. So one of the questions was, what is not trained fast on GPUs? It can, but the issue is since this is Swift for TensorFlow, it might not actually even work since this is so pretty new.
You know what I want to do in the meanwhile while this is training, actually?
Python?
Just for the fun of it. Let's go to Google Colab. Let's get a GPU environment. Let's just do this in Keras. It'll be like 5 lines of code.
Okay, let's do it quickly.
While it trains in the background, everybody, we're going to try doing this in like Python.
So here's the real question: Are we gonna use the TPU or the GPU?
Oh, we're using GPU. I'm not implementing recurrent neural networks in Keras on TPU. God, TPUs are already difficult enough to work with.
Imagine we just do it for the sake of it.
Okay, well, looks like I'm going to need an account to do that, wouldn't I? Well, I can always get my Chrome window. Give me a moment. Okay. So, Colab, research, Google.com, new notebook, and what do we want to call it? Let's just call it RNN test. Okay, watch how easy this is in Keras. This is gonna blow your mind just how easy this is. You literally do 2 imports.
Yeah, isn't this already a model for RNN from Keras?
Yeah, essentially.
So we're not just using that.
What? We're using a pretty vanilla implementation. I don't know what you're talking about.
So technically, you say this is in 5 lines. We passed the 5 lines.
Okay, well, I didn't mean it literally. I meant it figuratively. Okay.
You broke your
So,
promise, man.
forgive me.
So the data we load in, is it gonna be the same data set that we load before in Swift, or are we gonna
It's
compute?
going to be the one that we generated with your Python, the one that you wrote.
Okay. Huh?
Oh, that's weird.
Huh? Dense layer shape much have at least 3.
Oh, okay. We have to return sequences. Okay. Then we can create the model and compile it as well. Then we can load our data in.
Wait, what? Why are we naming this X?
What?
Oh, never mind. You already used X earlier, so it doesn't matter.
Yeah, it's fine. Okay, then I'm going to upload in the data.
Debug it,
Because...
believe. You might have it under debug.
Oh, no.
Nope, I guess not.
What happened, Omer? What did you choose the data here?
What? Oh, it could actually be enough. Okay, we name it. Yeah.
It's
Okay, so it's here.
literally here.
So I'm guessing it might be at the bottom.
Okay, you know what we're going to do? We're going to hide everything and then unhide these two. There we go.
That's a good way to do it.
Okay, so then once that's done uploading, we'll load it in, and we'll literally just do model.fit xy. That's literally all we're gonna need to do.
Someone has, but this won't be from scratch.
Well, yeah, we're just doing this to show you that it can be done, right? And then we're going back to our from scratch implementation in just a moment. Okay, so we have xy, and we're just
So
gonna do
someone mentioned technically a hackathon will work, but will just be as bad. Okay.
a Hackintosh or hackathon.
Hackintosh. What?
A Hackintosh, like a computer that's not meant to run Mac OS but is running Mac OS.
Okay.
See how simple this was?
And see how fast it was. Look at our loss. Look at that
And this
beautiful
isn't
loss.
even on GPUs. This is not using GPUs.
Can we move this to GPUs? I'm just very curious.
Sure, we'll do that in a sec. I just want to see if we can actually generate names. Give me a sec.
What?
Okay. Until then, let's also see.
Look, we give. Oh,
Okay,
look.
so Swift for TensorFlow with the 4 epochs generated 2, which would be B, and then E. So the two names it generated were B and E. So let's keep this going for like 30 epochs while we try out our Keras version.
Yep. Let's see what happened.
Until then, let's go back to Keras just to prove that the architecture works and it's not just something that we like messed up somehow. Another thing that I want to try is what happens when we integrate a masking layer.
Let's do that later.
Oh, sure. For now,
Let's try to do
just
let's
for
do
the prediction.
let's predict.
So I'm wondering how we would do that with Keras because we would have to feed in the whole vector over and over again. That's annoying, but it's the only thing we can do.
Okay, let's do that.
np.zeros, and this is going to be of shape 127, and then x 0 -1 would be 1. And then x dot. Oh, wait, one more thing we would need to do is change this. We'll have to retrain really quick, but
I was gonna say maybe we should go into GPUs.
yeah, sure. I mean, we'll need to re-upload the data then. Let's just quickly finish this, and then we'll try it out on GPUs too.
I don't think you need to, because just the one time will be different. I don't
Oh,
think it's
really?
gonna reload the whole thing.
Well, let's see. Yeah, it deleted the files.
No, oh my god, why is Google like this?
I mean, I don't blame them. They're giving us a different machine.
I thought they're just gonna attach the GPU to the, I'm guessing the Docker environment that they're using.
So Ayan's awesome fact says, this is why I normally use Keras.
That makes sense.
And that totally makes sense. But then, like, for example, let's just say you're trying to implement this thing called mixed, why am I forgetting the name for it right now? Mixed density networks for, like, handwriting synthesis. When you're implementing a network like this, using a framework like Keras is really restrictive because then you can't, like, for example, differentiate across the function. Well, you technically can, but it requires a lot of finagling with the framework. Whereas if you actually know how to use PyTorch and if you have experience with PyTorch, then it becomes a lot easier to do that sort of stuff. But anyway, let's just go ahead and try this out.
Yep. Let's see how fast this
Let's
changes.
see. Yeah, let's see how fast this is on GPU.
I don't think it's gonna be as
I
fast.
don't think it's gonna be that much faster, but I feel like it's definitely gonna be faster.
And then we found out we're actually not using GPU, we're just using the CPU all along. Never
Oh
mind.
wow, that's a lot
Never
faster
mind.
actually.
Never mind. We were doing completely incorrect. Can we just jump? Can we just pop this out to like 1,000? I feel like it got stuck at some moments. Was it
Yeah.
just waiting?
It was just the GPU was processing it so fast, Collab's output couldn't handle it.
That could have been the case. Okay, let's try to feed this back
Okay.
in. So maybe we need to create a function for this just to generate a name so we can run it a few times.
Okay, we'll do that later. For now, let's just get it to work. So. Okay, so m.predict x. So it's definitely not predicting end. That's good. What's the argmax? 0. Okay, so it's predicting an a, which is either a good thing or a bad thing. We'll figure that out soon enough.
We just found out A is the best character.
So we have an a. I'm just gonna manually build this for now because, yeah, but we'll make it better soon. -1 argmax.
Let's see what this will be. Not it? 11.
11. Okay, so we're definitely on the right track. 8. Okay, so we're not 0. Okay.
So we're back to 8. I'm guessing
We're
we're going to go
back
back to
to
11. No, 0.
Ooh, we're on A again. And we're on A again. And we're on A again. Oh, wait a second, I forgot to do something.
Are you increasing the size?
Wait a sec, I forgot to do something. Have to
Yeah,
do
I was
this.
wondering.
Yeah. It was a mistake. Okay, so then we gotta do 2, 11, and this has to be a 3. And then we go to 8, so 3, 8, 4. Okay. Then 4, what a coincidence.
It's lovely. 26,
And then
which
we
is
end. Okay, so that's good. So now we're ending here. So the results were
A, 11.
A, 11, 8, 4.
So
Now, if I knew the alphabet in terms of, like, indices...
Look, if I knew that, I wouldn't even need to do this. If someone can do it, that's pretty good on them.
Yeah. Okay,
Again, there are people that remember pi to, what is it, to like thousands.
Yeah, I'm very sure a lot of people would know this. It's just we don't.
Yes, we're not the best.
It generated Ali. Okay,
Oh,
that's a plausible
that's not
name. That's a plausible name.
Can we go back to alcohol?
Now, this entire live stream could have been like 20 minutes long if we had done this.
This is not PyTorch.
Well, yeah. We'll get back to that in a second. All right, but I'm just saying. Oh,
wow. We got something.
oh. Swift isn't. Okay, I feel like we might be onto something
Can
here.
you copy the last one?
824. Let's see what it generated there. I'm
824.
curious. It generated ice.
Technically,
Not bad.
a word.
Technically, it is.
Let's hit the second one.
Let's try this one. This one seems more plausible.
Huh?
18.
Huh?
Kinda? Is this a person's
Is
name?
this a name?
It's someone's last name.
Oh, okay. That's good.
Whoever this is, thank you.
You save our live stream. Okay, let's go to those longer, like that mass hit one. Let's see
Yeah,
what it was
like this
trying to.
massive.
Yeah, what is
Sure.
it trying to like do? Is it like a word or something? Huh?
Nakanau after. Naka now after.
I'll be surprised this is actually something.
It's not.
Okay. Okay.
But the thing that I'm surprised about is that if you tried to pronounce this, you could. Nakanalefta. Nakanalefta. Like, you could, right? In theory, you could name someone this. Like, it
Well,
understands basic rules of you can't just put like, two characters that you can't pronounce together beside each other. Like, it understands at least that much.
So the other one thing we gotta kind of make sure is that it might just be that it's only good at, say, some area of like name. Could just be North America, could be European, or does this include a number of like names from backgrounds?
Mm-hmm.
This one might be more accurate since it didn't hit the max.
It generated Ian Taro.
I'm pretty sure that could be a last name. It doesn't seem like it does seem plausible. Oh, it's at. It is someone Twitter. Wait, actually, can you go back? I think I saw someone the first and last name might be it. Oh yeah, it
Ian
is.
Taro.
Oh, I guess we created
Fascinating.
first and last names. It was.
This is
Okay,
actually really fascinating to play with.
so
But
for the fun of this,
mhm.
let's go back into TensorFlow, like the one on Colab. Let's actually create a function that will create the name, and they train it for 100 epochs and see what it could happen. And this could save us about 4 hours of live stream.
All right. Something I do want to try though, and I'm sorry that I want to try this, but I do. What if we tried doing this exact same thing that we just did in Keras with that huge PyTorch code base that we wrote?
We can, but are we gonna push it to GPU?
Yeah, that's what I'm thinking.
Maybe we can do. Yeah, we can do it. I was hoping maybe
Okay.
we'd do like another. Like the max skin as well. Or are we talking about like literally?
I just want to try this in Keras really quickly, see what happens. Okay, so what we're going to do now is train this like 20 epochs with gradient masking. So loss should instantly be a lot lower, which it is.
You didn't really load in the max. Is that okay?
Load in the what?
No. Oh, never mind. I was thinking of the custom one we created.
No, it's fine. The GPU is literally so fast, Colab's output cannot handle it. Anyway, okay, so we've got pretty low loss value. Let's see what our network tells us now. By the way, just so you know, the last time the perfect name that the network generated was Ali. So Ali was the perfect name. Now let's see what it generates. So we start off with an index of 0. Okay, I should really make a function for this, but we'll do that in a moment. Okay, then an 11. It looks like it's the exact same thing so far. Okay, 4. $23. Okay, this is different.
So I'm just gonna go on mute for a sec.
Yeah. 0. 13. If this gets too long, I won't be able to keep going. It needs to stop either in this time step or the next one. This thing really likes long names now. I feel like we should not have implemented that masking layer.
We'll see.
Yeah, this is a fan of big names.
Oh my god. I'm actually curious, what is this gonna predict?
There we go, it ended now.
26.
0, 11, 4, 23, 0, 13, 3, 17, 0.
Okay, there's a lot of 8s in there, but okay, let's see.
11, 4, 23, 0, 13, 3, 17, 0.
Can you not just copy that?
Yeah. Okay, let's try. So we go from Ali to Alexandra.
That's pretty perfect, actually.
Alexandra! Come on, that is the perfect name, according to the model. Alexandra is the perfect name, according to the model. Can you believe it?
Yeah.
Fascinating. Okay. I'm just really happy that this worked.
I'm guessing the longer the epochs, actually, no, not really. Again, we can train it for a little bit longer to see what happens. But before we go, can we actually implement the function?
Implement which one? Oh, yeah, definitely.
So we don't
Like
actually do this manually anymore?
Yeah.
Kind of,
it's painful.
It is very painful. It's not that difficult to do.
Yeah. So we're going to do two. One for the perfect name, and then another one for, like, random names.
Sure, it doesn't matter. As long as the last output is not 26, just keep doing it.
Yeah, exactly.
You need to initialize 0, 0 to -1.
Yeah. Well, 0, 0, -1.
Yeah.
So while true, we simply do prediction is m.predict on x, 0, -1 argmax, and then we do z equals np zeros 1, 127, z 0, 0 prediction equals 1, x equals np dot concatenate, x z axis equals 1, and then return, or we can say predictions is this, predictions dot append prediction, and then return.
And then also
predictions.
if prediction equal 26, we break.
Good idea. I did not think of that actually. Break. Okay. So we should be able to just generate the perfect name instantly now.
Yes. And of course, numpy.
Concatenate. Not concatenate. Okay, there we go.
So
it's
now what we need to do is take this. Okay, can you move G up a bit?
What?
Can you please move G
up?
Oh,
yeah. This is what happens when you write messy code in a collab notebook. Everything is everywhere.
I know for a fact that we're going to hit this issue. Can we move G up now?
Yes, I can move it up. Okay.
There we go. Can we also give it a starting letter as well?
What?
Let's give it so we can define what the first
starting letter is.
Yes.
So we're going to define two versions now. There's two more versions. So there's going to be one that we can prime, and then another thing. So we can prime it with a starting sequence of multiple characters, and then the next one will be what do you call it? Forgetting what it is. Oh yeah, and then just start from scratch, but with a temperature, so you can generate random names. All right, let's try this out. Let's see. Okay. So in order to do that, let's do the priming sequence one first. Generate perfect priming primer. Okay, so then x is equal to np.zeros 1 len primer 27, and then for I in primer x 0, 0 g dot index x equals 1. What?
Look, I'm just thinking of being a Frisian right now, but it's okay.
We don't have
I
time
will
to
just
think about
convert that
efficiency.
into an n and then minus a from it.
Let's just keep it simple for now, okay?
It's fine.
All right, and then I
Index
think we
over.
can just copy and paste this exact same code.
Well, yeah, we know what the prediction. The started farmer, by the way.
Yes, very good catch.
But we need the index.
What? I feel like this should just work.
No, it wouldn't.
Why not?
Look what we're returning.
Oh, well, yes, of course. Wait,
So just do a simple for loop.
what is wrong with what we're returning?
Okay, so do you see at the very end, line 30, we're going to a list of G and picking it out.
Ah, yeah.
So just do the opposite here. Do a for
Yeah.
loop.
Okay, or we could do it the
Yeah.
inefficient but simple way
Yeah, that's what I'm
of
saying. Just do a
G
for
dot.
loop and make that. Yeah, see?
Nice.
Sometimes
Good
it's
catch,
good to
man.
be.
Good catch.
Sometimes
Very
it's
good catch.
good. What the? What is not a list? What? What is it for the now?
20.
20.
Huh.
Oh, is I supposed to be? I thought I is supposed to be the index. Oh no, sorry, I underscore index.
This is weird.
Huh? What? The. Can we print out exactly what it's trying to do?
Oh,
You found the issue?
found the issue.
Was that X
We
or
were
I?
okay. So for ba, it thinks
Bana.
the perfect name is Bana,
Bana.
which
Okay.
I mean, it sounds pretty plausible. I
What
feel
happened
like.
to be here? BBAHE. Okay.
Yeah. So Bana is a name.
Okay. Okay, there we go. Let's see if we just get the one character.
But heal.
Okay. Do Tammy.
Oh, I forgot capital T. Tanika, Tan M, Tanmari, still Tanmari. Oh, Tanmaya, that one, that's pretty plausible.
Tammy. Yeah, a
Yeah.
lot of people do carry that anyways.
Let's try.
Can we do it with 0 in length? This should work.
Oh,
Come on. You know what we can do? Just lowercase it right away.
oh yeah, I could pretty easily do that, but let's not.
Nice.
Yeah,
0.
it won't work with a blank. You need to call the generate perfect name for that one.
Okay. Can we go back up? Let's train it for a bit longer. Say 100 epochs, since this takes like seconds to do.
Let's do 60. I don't want to overdo it.
Okay.
And
let's see what the loss is.
let's also just since we have so much compute power, we might as well
Are we gonna scale this up?
yeah, do multiple layers.
I
I feel like we have nothing to lose.
feel like we might as well.
The GPU with multiple layers is faster than the CPU with a single layer.
Yeah. I just found it very hilarious that we tried to do everything from scratch, and then we found out we can do everything in 10 lines.
If you think about it, the first 4 hours of this live stream were essentially just trying to get it to work from scratch, which we kind of did, to be totally fair. Like, if we take a look at the Swift for TensorFlow implementation, it is now generating...
Can we do this? Can we make it to 60 epochs and let that train in the background?
Yeah, sure. Totally.
Let's see what
Let's see if
happens.
Swift for TensorFlow gets to somewhere as well that's also not terrible.
Sure. It is getting better.
Yeah.
Oh, it got
Looks
to
like our
1.
Keras model is also doing pretty well.
Wow, it's gonna get to maybe pretty low loss.
Yeah.
Watch
At
it
the
hit
same
like almost
time,
50%.
at the same time, we don't want it to just like memorize every single name in the data set, right?
Right, actually.
Because again, we have no validation data. It doesn't really. I'm not even sure if it makes sense to have validation data for a character. I mean, it kind of does. But still,
how are you gonna really do that?
what?
I'm trying to think. How are you gonna validate against names?
Yeah, I'm wondering. We could literally just split the X and Y datasets into two and just keep one as training, one as testing. But I'm
I
not sure if that would
guess.
make sense. Ion says you can specify learning rate, decay, and epsilon to make it better. I do agree, but then again, hyperparameter tuning takes a very long time. That's not something that we want to do on the live stream. But we can try adjusting things. The thing is, for now, the default parameters work so well that we got to 0.86. So I don't really
Okay.
think we need to.
Let's do this now.
Let's generate the perfect name
name.
first.
What is the damn? I want to know what this perfect name is.
Okay, so now according to the superior model, the perfect name. Why
It's
is it
going to
taking
be.
longer?
Okay. I looked at the GPU slow for one petition.
That is weird that it's taking that long. Alexandre.
And it's all the same thing.
Pretty much. I mean, it's a character off, but it's still a good name.
Can we
Now
do? Yeah, let's do prime.
let's
Let's do.
try
Yeah.
Bahal.
What?
Bahal.
It's a different name.
Bahi is just Bahi.
Do all.
Yeah, just Bahir.
Yay.
It's like
Do
just end
OM.
it there. What?
OM.
Oh, Tanya. Okay, not bad. Tenmari. Oh, come on.
You're not gonna get your name. Oh, actually, you did. Do OM.
Well, no, that's because it just decided, okay, just end it at 10, right? Omar.
That's pretty good, actually.
Pretty
Omar is
close to your
very
name.
common.
Pretty close. Let's see what happens when we do OME. OME.
There we go.
There we go.
Let's do then ESS.
ESA.
Oh, sorry. Let's do
Okay.
Jack and see what happened.
Oh, well.
Lowercase, man.
Why do I keep doing this?
Lowercase, man.
Hooray. It knows what to do.
I have a lot of background noise, so I gotta mute.
No worries. But yeah, this is really interesting. Now let's go ahead and do that temperature thing so we can generate like lots of random names. So generate random name, which will essentially just be this, but NumPy choose random with probabilities. NumPy random choice. Okay. So I think we would just do NumPy random choice range 27. You only want to pick one, and the probabilities are over here. I feel like that should work, but there might be an issue with that. Maybe I need to do this. Yeah, Grigfith. Not too
Is that a
bad.
name?
We can try. We can check that out.
Good fit? I don't know. I guess.
Nicholas.
That's technically a name.
Nicholas is a name. Yeah, we
Definitely a
can all
name.
agree that Nicholas is a name. Yeah.
Let's do it again.
Earl, definitely a name. Trini, kind of a name, I
I
guess.
don't know if that's a name, is it?
Let's
Could be a
check.
name. Oh, also, can we go
Tiny
back to Swift? Let's see if it's done.
kind of is a name. Very rare. Swift is still going.
So going, okay.
But it looks to be achieving essentially the same loss numbers that Keras was getting. Like, if we take a look, Keras was getting 1.4 here.
But we're also doing different mode layers. Keep that in mind.
Yeah.
So it might have just done a much better job.
You're right. Beody, this feels like it could be a name.
So you want to do something overkill?
Yes, Beody is a name. Yes, I do want to do overkill. Tell me
Okay,
about
let's go back
overkill.
up. Let's just add like 3 more layers, just for the fun of it.
Are you sure you want to do that?
Let's just add more layers. Screw it.
All right, let's see.
Let it go down to 26.
All right. Now, one thing I do want to say, though, just for everybody watching the live stream, more layers does not necessarily always mean good. Okay,
Some might actually mean worse.
We're doing this for educational purposes, not because it's necessarily a good thing to do. But it's always possible that the model ends up generating good names. More than likely, what will happen, though, is that the model will just end up memorizing every single name in the data set, and whenever you give it a certain sequence of characters, it'll just generate whatever usually comes next after that in the data. But it's worth a try. It seems like loss is already stagnating. Yeah, I don't think these 2 layers are going to help at all. In fact, they're only going to make it worse. Now,
I did tell you to reduce the numbers.
If we were to implement a highway layer, that might help things. But implementing highway layers in Keras is incredibly difficult. So let's stop training and just remove a layer or 2.
Can we not reduce it down to 34, 32 from 64?
It's 64. I'll keep it at 128.
No. Make another layer and put that to 32.
Sure. I think the problem is that the gradient space is going to be so spiky when you have these many layers that it's just never going to end up in a minimum.
We'll see. You can always just freeze the layers.
Like, train some and then freeze them.
And then train some more and then freeze that.
I don't think that really makes sense.
Yeah, we're doing overkill. Okay, actually, it's doing pretty decent now. I don't think, nah. We got down to 0.9 before, right?
Yeah.
Okay. Let's see if we get to that point or not.
I doubt it will. Wait, we got to 0.8.
Ah, 0.8 it is. So that's the number to beat.
I somehow doubt we're going to get to 0.8, but hopefully.
Well, we still have a lot of layers left. I don't know.
I don't think we're going to. It's already stagnating.
It's probably going to stop at 1.1-ish for the rest of the layers. But again, we could be completely wrong.
Yeah.
It might just be stuck at a local medium.
I mean, I can only hope we're completely wrong.
I just don't want Alice. I just want a different name for the perfect name, okay? That's it.
You know what's going to be funny is if the model always, from different initial random parameters and different architectures, always ends up choosing Alexandra as the perfect name. That says something about Alexandra in that dataset. Something about that sequence of characters
Might be.
excites the network.
Nice. I'm just a floating head almost now.
Okay, yeah, we're gonna stop training here. It's pretty terrible.
No. Let it just finish.
All right, let's see what Swift for TensorFlow is doing. Still going.
Still going hard.
Still going strong. If the Swift for TensorFlow model works and it actually generates good names, at least the point of this live stream will have been fulfilled.
And it will have been about 5 hours of showing.
Yep. We're gonna probably stop this at 5 hours.
Probably.
They're having a pretty good discussion in the chat around hyperparameter tuning, which is good. Abhishek, thanks for your insights on hyperparameter tuning. I do agree with what you're saying in terms of using, like... Well, I have not heard about using Jenkins for hyperparameter tuning. Have you heard of that, Omer?
Are we just using like a pipeline to check what parameters are good?
I would assume that's what Abhishek means.
You didn't mention like DevOps, so...
Yeah, I mean, one thing that I do completely agree with Abhishek is that it is very difficult to do hyperparameter tuning like this, and And there are different pieces of software that help you do that. Things like Teapot or IBM Watson has Auto AI. These sorts of things are meant to help you do that. Okay, so a random name that this new model generates, and this is going to take a lot longer because it's deeper, but...
Okay. But I want to know the preferred name, okay? I just want the preferred name to be something else for once.
Alright, I'll be right back.
Okay.
Or maybe I won't. No, it's fine.
It's going to probably be done within a couple minutes.
Yeah.
Huh?
Rylani.
Okay.
We should search this up
That
in a
might be
different
a real
tab.
name.
It is, but without the last E.
Oh, okay. Well, the last thing. Okay, let's see what the preferred name is now.
Yeah.
Watch it just be the exact same thing as before.
If it's still Alexandra, somehow Alexandra happens to be mathematically the perfect name for this model. And I feel like the reason is because it's long, and the gradient descent algorithm wants the names to be longer because it's more used to predicting a character than it is to predicting a blank label.
Yeah.
But at the same time, the individual characters might just generally appear more in names.
Can you do this? Can you type in Alex and see what the ending will be?
Yeah, it'll be
Actually,
Alexandra.
yeah, wait. What am I thinking? I'm like, it should work. Can we do the mail version of it and see if it finishes up?
Yeah. The what?
The
The
mail
Swift for
version.
TensorFlow version? Yeah. So
Oh,
it barely ever hit the max length. That's good. So the model knows when to stop its sequences. And let's see what this one was.
let's see.
So the model generated Brishrana. Not too bad.
Can we convert this to a string, please?
Yeah. I'll do that.
Just literally type in string in the beginning. Oh, join.
Or
Okay.
Brishrana.
Is
Not
that?
totally off from what would be expected.
Okay,
Like,
wait.
if
What
you were
is
to
this?
name someone this, it wouldn't be too bad. Anira,
It's not bad.
again, not the greatest, but definitely not, like, incomprehensible. And Kanila,
So economically, you can.
I feel like you can see that it's learning a pattern, but it's not memorizing the... Okay, yeah, this
Okay,
one was
that's
off. This is
completely
off.
messed up.
That was definitely off.
Next one.
What I will also try, by the way, is not dividing the result and just getting the softmax.
Okay.
So I'm going to rerun this. We'll
It's
try
gonna
one
take.
more.
It's gonna take forever, man.
Yeah, but like while we're doing other stuff. By the time we reach the 5-hour mark, it'll be done. 10 minutes. And then,
5-hour mark is in 10 minutes. Okay.
yeah, okay, so we've got 10 minutes to run this. I feel like we can do it.
Honestly, never used DevOps or check. Never mind. Just reading some of the comments.
Okay, so here's my thing. Before we end the live stream today, there's one more thing I want to do. And it's a bit of a long shot, but hear me out on this one. What we do is we use PyTorch XLA, and we get this model running on a single TPU core. So we don't need to do like synchronous management of TPUs and this and that. Just a single TPU core. It's going to be slow, but we get it to train on a TPU. Just to be true to what the original purpose of this live stream was. I feel like we can do it now that we've got this down.
That's a little bit overkill, but okay. Can we do it in
Let's
10
do
minutes?
it. All right, so let's do this, everybody. We will be back in like 5 minutes, and we'll go ahead and implement that PyTorch model. All right, stick around because I'm sure you're going to be fascinated to see what happens when we try and implement this on a TPU. Okay, finally we are back, and if we take a look at how our Swifter TensorFlow model has been doing, it's still going down. We're not really saving the model between iterations, which is why it's taking a lot longer than it should. But regardless, it is still training. Now, apart from that, though, if we have any questions in the chat, we can definitely take those up now. And then what we will do is we will pause until this model is done training, show you this model finally, and then we'll be done with the live stream for now. And then next week, we will continue with the same topic, or whenever we're holding the next episode, maybe next week, maybe before that. We will continue with this episode, show you how to finish this name generator, maybe even show you how you can use conditional RNNs to actually generate specific genders of a name or whatever, something, these sorts of like customizations. But for now, we would love to answer any questions you may have. So while this trains.
So maybe next time we're talking about conditions, we can do maybe, is it a female? Which area is this from? So is this like is this like an English name, Spanish name, or even like the different version of Alex, Alexander, or like literally, if it's Russian, it is Spanish, because they have different ways of spelling it.
The
Or even
etymology of
pronouncing
the
it.
names.
Yes.
So we have a question saying, if you could in a later video, try using a more advanced architecture than RNN for text classification generation. So we're not using vanilla recurrent neural networks here. We are using LSTMs, which are relatively complex machines. Nowadays, when you take a look at like transformers and things like this, they might not look that complex, but they are. So we could totally, in another episode, take a look at using transformers for something like this, but we're not sure about that just yet. All right, so we ran it for many more epochs. This is the output we got. Let's take a look at some of these names. I don't think they're going to be particularly great, but let's see.
It's probably not going to be. Let's see.
Yeah, it's probably not. Let's see. Yeah, kind of, I guess.
What happened? I feel like
Kind
the
of
one
ish.
layer did the. Oh, we're doing this.
Scene. Yeah, no, it started to like severely just overfit to always predicting the end. Sharon? Okay, not bad.
Let's see. Maybe this one. No.
Util. Definitely not.
Let's do the last one.
Yeah. Lim.
Kind of.
Not great, not that bad either. Well,
I like ice.
yeah, the ice
That
one was
better.
pretty nice. The ice one was pretty nice. So here's what I'm planning on doing. We'll hold a follow-up to this episode before we do our next episode of this series, and in the follow-up, we will continue this project and sort of bring it to like a completion point where we can say, you know, this network can generate according to a condition, like I want a male or a female name, or the network can classify genders of names, things like that. And then from there, I think we can say, and also get it to run on PyTorch instead of having it in Keras. After that point, I think we can say this is done, and we can move on to the next episode. But for now, since it's been 5 hours on the stream, I feel like that's enough for this episode. Again, any questions, feel free to send them in. We still have a couple of minutes before we go. Anything you wanted to expand on, Omer?
Not really. Maybe next episode we can do a better, not a better job, more on this condition, the actual input, more
Yeah.
than always the best random name we can ever create.
Perfect.
Let's try to do like what is the best name, say if you're Spanish or you're from the Middle East or European. Kind of condition it to that.
Yeah. All right.
I'm very curious if we put in, let's say, because some language, some countries, the length of their name are like crazy long.
Yeah.
So maybe we should try a different model set with longer names, and see what happens.
Maybe.
Does it still pick those longer names to be what get the perfect name, like as we see with Alexander? Since
Let's see.
it is a long name, but at the same time, it's not the longest name that we have. It
Yeah.
might be.
Christopher's the longest one, by the way.
Okay, good to know. I'll be shocked if, say, we have much longer characters and Alexander so is the first one, because that will just show that it might just have a lot of similarities with the name that's currently in there. Because I think these are all basically from one area. I'm not sure how the data set is broken down into when it comes to the names. Does it
Yeah,
include names from like the African country, the Middle Eastern country, the
probably
European?
not. These are
Yeah.
all like Western names.
So I wonder what happened once you mix all those together, and maybe that's something we should do next time.
Totally. All right. Sounds good. Well, I hope this was insightful for everybody and the debugging process was helpful and you were able to figure out that many, many hours can be wasted when you think that an issue is in one part of your code when in reality it's in a completely different part of your code, somehow being obfuscated by layers of frameworks and gradient descent calculations and all these things. So hopefully that was insightful. One thing I'm going to do really quickly is stop sharing my screen with Omer and switch over to Zoom so you can see the both of us big screen. Wonderful. All right, so that concludes this episode of Live Coding. And once again, any more questions, feel free to put them in the comments. We'll try and get back to as many as possible. If they're in the live chat, then we can't get back to them after the actual recording. So if we haven't gotten to your question, but you want it answered, put it in the comments of the recording of this video once it's up after this, and we'll try to get to it as soon as we can. The next episode will be held soon, and you'll be able to see on my social media when exactly that is. And again, if you have any suggestions of what to cover on the series or anything of that sort, feel free to leave that down in the comments below as well. Apart from that, anything else you wanted to say, Omer?
No, that's everything.
Wonderful. All right, so thank you very much, everyone, for joining in today. Hope you enjoyed, and we will see you next time. Goodbye.
Bye, guys.
We're done.